This video has everything you need to know for the AMC 10, from recursion to Markov chains to Vandermonde's identity, Euler's theorem, cyclic quadrilaterals, and many more. And in addition, we'll also go over strategies to approach these types of questions. Things that are not maybe super formalizable, they're not like a formula, but there's hidden techniques that the best problem solvers know and they use to tackle these tricky AMC problems. But first, let's start off with the basic concepts in combinatorics. Factorials and factorial is just the product of all the numbers from 1 to n. Okay, so permutations, some basic formulas. If you're arranging n objects in a line, that's just n factorial, right? You got n choices for the first object, n minus 1 choices for the second object, so on. The final object is fixed, it has only one choice. And let's say now it's a circle and rotations don't matter. What we do is we just take n factorial arrangements and divide by all n possible rotations of the thing. For example, 3 people, there's 3 choices for who could be on top. So we divide by 3. And let's say reflections also don't matter. Then we just divide by 2, right? You either have something normal or reflected. So you overcount everything by a factor of 2. So you just divide by 2 here. Okay, and then the permutations formula. If you want to take k objects out of n objects ordered, it's just n times n minus 1 all the way until n minus k minus 1. Basically, you just start at n and then you multiply by the number down and you do that a total of k times. And intuitively, that makes sense, right? You have n choices for the first object. Now you only have n minus 1 choices for the second object, and so on. Okay, now word rearrangements. Now this is actually super useful for beyond just words. So now let's say you have like a word. Let's just say we have a very simple one. Let's say we have ways. It's just going to be 4 factorial because just like the book's problem, we just have 4 things. We rearrange them. But now sometimes we might have duplicates in our word. So let's say we have something like paper. So now what we would do here is see there's 5 letters, so 5 factorial arrangements, but now there's 2 p's. So if you think about it, you can call this p1 and p2. And if these p's were different, we would have 5 factorial ways. But the p's are not different. So whenever p1 and p2 are swapped, we're basically doubling the number of ways we should be counting. So we divide by 2. And this logic kind of continues on forever. In general, if you have a word which has, let's say, d1 of the first letter, d2 of the second letter, d3, so on. So basically, you look at all the letters that occur more than one time, and you take n factorial, where n is the total number of letters, and you divide out by all the duplicate number of letters, the number of times they occur, factorial. And this is really useful because it's not just true for words. In fact, oftentimes, whenever you're trying to order something, these word rearrangements is very useful because just when you're ordering some kind of string, which has, different types of characters in it. And sometimes you can also use it in other scenarios with like blocks, for example, or maybe you're trying to, I covered some examples of this in the previous video in the Mastering AMC 10-12 series, which you can check out. So yeah, all these concepts I'm going over very briefly here. I cover them much more in depth with many examples in the Mastering AMC 10-12 playlist. You can check out the link in the description. But now let's move on to combinations. So yeah, combinations is where the order does not matter. And some keywords, permute, order does matter. They imply, it's a permutation versus choose, select. These imply combinations. So let's move on to the combinations formula. And it's very similar to the previous one, where we had over here, which is n in factorial over n minus k factorial. Except now we divide by an additional k factorial. So if we have, let's say, 8 spots, 8 people, and we're choosing 3 of them to, be the leaders or something, and the order of the leaders doesn't matter, we could just say 8 times 7 times 6. Oh, but the order of the leaders doesn't matter. We overcounted by a factor of 3 factorial for all the leaders being ordered. So that's just the gist of the combinations formula. In general, it would be n choose k, which is n factorial over k factorial, n minus k factorial, which is often used in this way, which is kind of what I showed here. Yeah, and this is an important identity. We'll cover it later as well. N choose k equals n choose n minus k. Intuitively, you should understand why this is true. Choosing 3 objects out of n is the same as choosing n minus 3 objects not to have. There's like a equivalence. The number of ways to do each of them is the same. So these quantities are equal. And you can also see this from the formula, right? These two will just be switched. Okay, now moving on to subsets. let's say we have a subset and that has many elements in it. And let's say 4 elements, just for the sake of simplicity. There's going to be 2 to the 4 subsets. Why? For each element, you've got 2 choices. It's either in or out. So we just multiply 2 times 2 times 2 times 2, 2 to the n in general. And be careful, if it says proper subsets and we're not including the empty subset, then we have to subtract 1. Because, we overcounted the empty subset. Okay, now probability you're probably familiar with. Desired outcomes by total outcomes. That will give you the probability, the chance something happens. And okay, now we're going to move on to something where oftentimes people get confused about. And that's in probability. Does distinguishability matter? So let's say we're trying to say, okay, we're trying to pick, we have 5 books, and we're trying to pick our 3 favorite books. And someone randomly selects 3 of these books. What's the probability you select the 3 favorite books? And okay, so if you think about this, let's say the order of the books doesn't matter. Then it would just be one way to choose your 3 favorite books, because the order doesn't matter, divided by 5 choose 3, which is just 10. 1/10. Okay, but then what if the order does matter? Then there's going to be 3 factorial ways to select your 3 favorite books, including ordering. And then just going to be 5 times 4 times 3 ways to choose the 3 books from the 5 books, because the order matters. But take a look at this. This is just 6 over 60. Same answer. You probably noticed, like, okay, it doesn't really matter whether the favorite books have an ordering or not. Because if there is an ordering, just make sure to be consistent here. You don't want to say the favorite books has an ordering, but the books we're choosing originally, the denominator does not have an ordering. As long as you're consistent, you're like, okay, the 3 favorite books has an ordering, denominator has an ordering, or the 3 favorite books does not have an ordering, the total number of ways does not have an ordering, you'll be fine. And be careful, because this whole thing, this method is kind of like the safe way to go about it. You're never going to get wrong if you account for order. But if you do this, it's also okay as long as each ordering is equally likely to occur. So in this case, yeah, 1, 2, 3, let's say, would have the same chances happening as 1, 3, 2. But for example, there might be some cases where, for example, some values, they might have different number of ways. Like this case might have 5 ways, and this case might have 9 ways, let's say. So then now you cannot just be like, okay, one of these 2 works, so the probability is 1/2, when clearly this has more orderings. So you can only use this kind of shortcut when your cases have the same number of ways of happening. And yes, there's one way you can have, let's say, book A, then B, then C. And there's also one way you can have book A, then C, then B. So it doesn't really matter in this case. Okay, so now probability for independent and dependent events. This is when you're trying to find independent events, you literally just multiply the probabilities. It doesn't matter. Now, when they're dependent, sometimes you have to do a little bit of casework. So let's say you have an event A. Let's say there's just very standard types of problems. On Saturday, there's a 60% chance of rain. And then on Sunday, if it rained on Saturday, there's a 50% chance of rain. And if it did not rain, then there's a 40% chance of rain. So you just take the cases and add them up. Pretty simple. But sometimes you can use some symmetry logic and see that, okay, even though it's dependent, it doesn't really matter. Like, it's all symmetric. And a good example of that is, let's say you have 7 runners, and you're trying to see, okay, what's the probability the 2 people who finish first and second are Alex and Bob, let's say. So technically, the second place person is dependent on the first place person, but it's symmetric. So it doesn't really matter where Alex or some other random person gets first, Bob still has the same chance. So technically, they're dependent, but it doesn't really affect the probability. So we can kind of treat them as independent events. So yeah, here you just multiply the probabilities blindly if they don't affect each other. And here you sometimes will have to do casework like I mentioned here. And moving on to casework. And this is the thing where, you can have really easy casework problems, and you can also have really, really hard casework problems. Like if you saw the AMC 10B number 19, that problem was notoriously hard to do with casework. It's super easy to mess up. A lot of cases. So a common question people ask me is, how do you do casework organized? How can you not make mistakes while doing casework? And here's kind of the way to go about things. So there's this one problem earlier. I'm not going to solve the problem fully, but it was like, okay, you have a bunch of rooms and there's a couple cases, or let's just take a really simple example. Okay, let's say you're trying to find all the solutions to this. So I know for those of you who know stars and bars, this is like really easy, but let's say you didn't know stars and bars just for the sake of demonstrating a technique. Let's say you only knew casework. So here's how you make mistakes while doing casework. You just try to find out, and let's just say x, y, and z are all positive. So here, to make mistakes while doing casework, you're just like blindly thinking, okay, what could possibly work? We could have 1, 2, 2. We could have 3, 1, 1. We could have, is there anything else? Who knows? Maybe. But in this case, it was pretty simple, right? We got all the cases by just thinking, okay, what more cases could we possibly have? But let's say this was like 8 or something, right? You see how easy it would have been just to miss a case out of nowhere? Because we're not really going in an organized manner. We're just trying to list out all possible cases that could potentially work. And we're not really going methodically here. We're just trying to pick some random cases that we think would fit it. And it's very easy to miss out on a case. So a more logical way to go about this that will prevent you from making mistakes is you could do casework on one attribute and vary that one attribute. And for example, what I mean by that is in this case, you could be like, okay, if x equals 1. Now what about if x equals 2? So on, x equals 6. And then you can be like, okay, x equals 7 and 8 don't work because y and z have to be positive. You see how this way, I'm getting every single possible case. I'm not just going to randomly miss an ordered pair, 3, 3, 2, because I was just listing them randomly. I'm going in a methodical way. I'm capturing every value of x. So it's much harder to make mistakes this way. So really just fixing one attribute, varying that, like we did here, x. And then if you need to, you can also do subcases for y. Like, for example, you could be like, okay, 1, 6, and then 2, 5, and then 3, 4, so on. And I know obviously this is a super simple example. Real AMC problems are going to be much harder than this. But the same general strategy still applies. Okay, now we're going to talk about complementary counting. And this is a technique where we look at the opposite of what we're trying to find. So like and this is really useful when you have at least. So a very standard example is how many ways are there to get at least one head when you flip 3 coins? And this is very standard, right? There's 2 to the 3 total ways to flip the coins and 1 way where you get no heads, so 7. So you see how we kind of go opposite. Doing casework is still possible here, but it would be much harder. So there's kind of these two kind of, things you want to balance. Casework, complementary counting. Casework, right? You're looking at all the cases. Complementary counting, you're looking at everything that doesn't work. Sometimes you have to do casework and complementary counting. Okay, so you find the cases that don't work. But oftentimes there's, let's say, 10 total cases, let's say. 7 of them work, 3 don't work. So in this case, it's much easier to look at the cases that don't work because there's less of them, so less work for you. You kind of have to predict, okay, how many cases are there going to be when I just do direct casework? And how many cases am I going to get if I do complementary counting? So you have to decide and judge which will be less work, which will be faster and easier to implement. Now onto the principle of inclusion, exclusion. So yeah, so this is a kind of complicated notation, but it's really just common sense if you think about it. So we're trying to find all the ways such that where A and B work, A or B works. So naturally, it's very simple. You find all the ways A work, then you find all the ways B work, and then you just subtract the ones where they both work because that was overcounted. And this is very similar for three values. And this is kind of like an extension of casework and complementary counting if you think about it, right? You find all the values this work, you find all the values this work, you find all the values where this work, but you overcounted the values where this works, and you overcounted the values where this works, and you overcounted the values where this works. But now you undercounted the values for this work, so you add it back. So you see how we kind of alternate? We add all the values where exactly one of the things are true, then we subtract all the values where 2 of the things are true, and then we add all the values where 3 of them are true. And the same thing generalizes, and this might look super scary, but it's really the exact same thing. Just like earlier, if you have like 4 events, let's say, you find the number of ways where each of the events occur, and then you subtract the number of ways where 2 of the events occur, you add back the number of ways where 3 of the events occur, and you just continue this same pattern forever. And again, I have a whole video on this, covered some examples. So if you want to check that out, you can check out the Mastering AMC 10-12 playlist. Much more detailed. This is just a review video. This is not meant for you to learn all the concepts on the last day. Okay, so now we're going to move on to stars and bars. So we have stars and bars, the number of ways, and this is basically like, let's say you have n candies, and you're trying to give these to 8 different kids. Let's say 3 kids. Let's say we have 6 candies, we want to give them to 3 kids. So there's a way to do this with casework like we saw earlier in the x plus y plus z equals 8 problem, but there's a much slicker solution with stars and bars. So basically the idea is that we have 3 children who are giving the candies to. So we're going to place 2 bars in between them. So now what we can now say is that because we place 2 bars, let's assign all of this to child number 1, all of this to child number 2, and this to child number 3. So now, really all we have to do is find the number of ways to place these 2 bars, because the number of ways of placing 2 bars is equivalent to the number of ways of distributing the candies. So how do we do this? Well, our handy word rearrangement formula. There's 8 total objects, so 8 factorial by 2 factorial, 6 factorial. Because you have 2 bars and 6 circles, or people, which represent in this case. You see how our word rearrangement formula is coming back at us to help here? Okay, so now let's move on to like some restrictions. So in the AMC 10, you're never going to find, or it's very unlikely for you to find a completely direct stars and bars application. Sometimes they'll be like, okay, every child gets at least 1 candy. In which case, it's very simple. Well, all you do is you'd be like, okay, this candy goes to child 1. This candy is assigned to child 2. And this candy is assigned to child 3. And now we just do stars and bars with the remaining candy. We just assign 1 candy to each of the 3 people and be like, okay, now we have 3 candies left and 3 people to distribute them to. So we place 2 bars and then 5 choose 2, or 5 factorial over 2 factorial, 3 factorial would be our answer. So that's kind of the stars and bars for constraints, and even this was a super simple constraint. There's some really clever applications of stars and bars. It's one of the most creative tools. And let me just show you one more cool application, I think. Let's say you have 10 people in a line, and you're trying to choose 3 of them such that no 2 of them are sitting next to each other. So without this condition, it would just be 10 choose 3, pretty simple. But now we have this condition like, okay, there has to be at least 1 here. There has to be at least 1 person here. So there's a really cool trick here. We have 3 people. We're trying to choose the locations of 3 people, or choose which 3 people to select. And we have these so basically what we do is we have these place marks, like 3 people, right? This is where the 3 people go. So now what we do is we have 7 other people. What we're going to do with those 7 other people is place them between our designated spots. So let me just say this. Let's assign all 10 people numbers from 1 to 10. So now we're just basically trying to choose which numbers we're going to select. So what we do here is we just say we have 7 other people to place in between these people, in between the people selected. So this is just a distribution problem using stars and bars. So we can place anyone here. We can place the 7 people in these 4 locations. But there has to be at least 1 person here and at least 1 person there. So it's like we're distributing 7 people into four regions, except we have to have 2 of the people going here and here. So to do this, we just use stars and bars, except we subtract 2 people because we have to assign them to these 2 regions. So now we just have 5 people distributed amongst 4 regions. That's just 8 choose 3. So that's the number of ways to put people, to pick 3 people such that no 2 of them are sitting next to each other. And just to summarize what we did here is we're looking at our 3 spots. We're trying to see, okay, we got a bunch of people in this line. Where are these let's say these are all in a fixed order, right? Where are the spots selected going to be? Let's say 10 people, right? So in order to find where the spots selected be, we're like, okay, let's say our spots selected here. And we have to somehow fill people in between them. And then finally, at the end, whatever we filled up, like let's say we put one person here, 2 people here, 2 people here, and then let's say 5 people here. That's just an example. Now, that will give us the numbering of these 3 people. And I covered similar examples like this in the book, Mastering AMC 1012. You can check it out in the description. Okay, now we're going to take a look at combinatorial identities. And this is the one we already covered. And here's a binomial identity. It states that n choose 0 plus n choose 1 plus n choose n, all the way until n choose n, is 2 to the n. For example, 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3 is 2 to the 3. Why is this true? Imagine you have 3 objects. You're trying to find how many subsets of them there are. There's 2 to the 3 subsets because 2 choices for each object. But there's also, you can also count the number of subsets by saying, okay, you can either choose 0 objects, 1 object, 2 objects, or 3 objects. So that's where this identity comes from. Now there's an odd even identity, which is super useful. Let's say you're trying to find 7 choose 1 plus 7 choose 3 plus 7 choose 5 plus 7 choose 7. This is just 2 to the 7 by 2. So imagine if this was 7 choose 0 plus 7 choose 1, everything all the way till 7 choose 7. That would just be 2 to the 7. But because we have odds, we just divide by 2. It's a really cool identity in my opinion. Now on to Vandermondes, and this is it's come up recently on the AMC 10, and it's been kind of trivializing problems. And basically all this is saying is, let's say you have 3 choose 0, 4 choose 3. And then you add 3 choose 1, 4 choose 2. So on all the way to, let's say, 3 choose 3, 4 choose 1. Oh, whoops, that is not what I meant to say. Here. Notice how each time you have 3 and 4, but each time these things add up to 3. And then 1 and 2. And all the way till 3 and 0. So we're like, okay, out of these 7 items, imagine we have 7 items, right? Now, the first 3 of them belong to one group. Let's say it belongs to the blue group. And the next 4, let's say belong to another group. So what we're doing is like, okay, we're basically choosing 3 of these objects. Three of these things to pick. Another way of doing that is saying we have this first group. We can either select 0 from this first group and 3 from this group. Or we can select 1 from this group and 2 from this group. Or we can select 2 from this group and 1 from this group. Or we can select 3 from this group and 0 from this group. But this itself is actually not very useful. Why? Because we could have just done 7 choose 3 directly. What are we going to do writing this out? But here's when it is useful. And that is, they often do this trick. They've done it on the AMI and AMCs in the past, where they make this kind of tricky. Like they make this 2. They kind of use the above identity, this one. And then they make this like tricky. They make this a little bit, more nuanced. Take a look. Now we have, okay, choose 3 from this and choose 3 and 3 from this. Now choose 2 from this and choose 2 from this. All the way till choosing 0 from this group and 0 from this group. But if we use this identity here, we can rewrite it really nicely, and we can just make this all. We can just say, instead of choosing 3 items from this, choose 0 items not to have. Instead of choosing 2 items from here, choose 1 item not to have. And then at the end of the day, we realize what we're trying to count is just 7 choose 3. So yeah, keep in mind, Vandermondes, they often do something like n choose n choose r, m choose r, and then plus n choose r minus 1, m choose r minus 1, so on. And then the trick here is just realize that this is still Vandermondes just with this identity. And yeah, this is a special case, which is kind of what I was describing earlier. We have like 2 choose 0, or maybe not 2. Let's say 10 choose 0 times 10 choose 0, plus all the way till 10 choose 10 times 10 choose 10. This is just 20 choose 10. And that's the same thing I was describing earlier, but a slightly more specific case. Okay, now on to Pascal's and hockey stick identity. And this is Pascal's triangle, where each thing can be represented 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2. Each value is represented here. But really what we get out of this is Pascal's identity. And you're probably familiar with that each value is the sum of the two values on top. And if you use this, we see this cool little trick. Now, if you ever forget Pascal's identity, I like to do it is just think, okay, 5 choose 3 is 10. 5 choose 4 is 5. And then the next one is, what is 15? And then I'm like, oh yeah, 6 choose 4 is 15. So basically, you start with n choose r, you increase the term in the denominator first, then you increase in the numerator finally. That's how I like to remember it. I'm not going to go into the proof of this, but you can check out the book. It's in there if you're interested. It's a nice proof. You should check it out. So yeah, this is often useful for simplifying expressions. And now there's the hockey stick identity, which is quite useful. And let's say we have something like 3 choose 3 plus 4 choose 3 plus all the way till 20 choose 3. Now, trying to do this by hand, not fun. So what hockey stick identity says is this is just take the last term here, make this one bigger and this one bigger. So that gives 21 and 4. And the thing about this is you have to be very careful. You have to start at 3 choose 3. If you start somewhere in the middle at 5 choose 3 until 20 choose 3, you cannot just say it's 21 choose 4. It's only true when you start at k choose k and go all the way up till n choose k. Then it's n plus 1 choose k plus 1. And but what if you were trying to, let's say, find 7 choose 3 all the way till 20 choose 3? You can still use hockey stick identity. So the thing to notice here is the top part is 21 choose 4. But take a look. The stuff we're missing, 3 choose 3 plus 4 choose 3 all the way till 6 choose 3, is just 7 choose 4. So all we have to do is subtract 7 choose 4 from 21 choose 4. And we get a much nicer expression for this long thing. Okay, now on to rectangle counting. The general formula for number of rectangles of all sizes in a grid. Well, this is a really cool trick. You have m by n, so you have m plus 1 of these lines. And now you have n plus 1 of these lines here. So notice to get a rectangle, we just need 2 vertical lines and 2 horizontal lines. So we just do n plus 1 choose 2, and then n plus 1 choose 2. And that gives you the number of rectangles in this entire grid. And this is actually a really clever trick. Oftentimes they might throw you conditions like, okay, now what if you cannot have any rectangles here in this region? And that's just a matter of complementary counting, right? You can find the total number of rectangles, and then you can be like, okay, how many rectangles contain this square? Well, let's just say it's 1 square, just for simplicity's sake. Let's say the question asked, how many rectangles do not contain this square? So you would just find the total number of rectangles in this grid, and then subtract the number of rectangles that contain this square, complementary counting. Because it would be much nastier to try and find all the rectangles that did this. That would be a lot of casework. So how do we find the number of rectangles with this square? You just realize the same logic, that our vertical and horizontal line logic. This time, we have less choices for our vertical lines that include the black square. The second vertical line can be here, here, or here. The first vertical line can be here or here. So instead of 5 choose 2, it's just 3 times 2 choices for the vertical lines. Similarly, we have 2 choices for the top horizontal line and 3 for the bottom horizontal line. So 6 choices for the horizontal lines. So in total, we have 36 rectangles that contain this square. So you see how it all comes down to looking at the vertical and horizontal lines and seeing what must be true because of this condition. Okay, now square counting. This is also quite cool. The number of squares in an n by n square grid, and here it could be any rectangle. I know this is a square, but it could be like 4 by 6 or 4 by 7 or something. It doesn't have to be a square. And it also does not have to have these things also do not have to be squares. Okay, so square counting. The number of squares in this n by n grid is just 1 squared plus 2 squared all the way till n squared. Why is this true? Well, notice how there's n squared 1 by 1 squares, right? Just 1 by 1. Now, how many 2 by 2 squares are there? Take a look. 1. So you look at the the horizontal values and the vertical values. So for the horizontal values, you can either have this. The 2 by 2 square can either occupy this, or this. Those are the different the different regions the 2 by 2 square can occupy along the x-axis. And then on the horizontal axis, on the vertical axis, the 2 by 2 square can be this, this, or this. What I mean by this is, let's say we pick this as our vertical region and this as our horizontal region. Now our 2 by 2 square is just this, right? So for each choice of two squares on here, two sides there and two sides here, we form a unique 2 by 2 square. So it's just 1, 2, 3 squares there. And then 1, 2, 3 over here. So we have 3 choices on top, 3 choices on the left. In total, we got 9 choices for the square, 3 squared. And similarly, for 3 by 3, it's very similar. There's just 2 squared 3 by 3 squares. Why? Because it can either be like this, the square can either write like this and like this. Or it can be like this, 3 by 3 square, or like this. So in total, 2 squared choices. And don't just try and memorize this formula and be like, okay, I don't have to worry about the derivation logic. Because AMC problems are not going to give you this exact thing. They're going to give you a variation of it, a trickier variation. It's important to know how you actually get this. So when they throw restrictions at you, you're not just like, which formula do I use now? Okay, now path counting. Again, a similar logic to the previous thing I mentioned. You don't want to just memorize this and be done. So the number of ways to get from 0, 0 to mn, moving only right and up. So the key thing here is it's a very nice, kind of bijection correspondence. Imagine each right step as a r and each left step as a u. So now basically it's equivalent to saying we must have a string with 4 r's and 4 u's. So the number of ways is just ordering this, which is word rearrangements. Or you can also just do a choose 4. You choose 4 of the spots to be right. Yeah, and this generalizes to get m plus n choose m for any general grid. But oftentimes there are going to be restrictions. This is super common. Even at the AMC 8 level, they will throw restrictions at you very often. They'll be like, okay, you can't come in this square. And then often you have to do complementary counting, right? You would be like, okay, how many ways are there for me to go here and then go here using path sounding tricks? So you would just find the number of ways to get from here to here and then here to here. A very common standard pattern. Okay, now geometric probability is just basically if you have an infinite number of possibilities, you represent it with a square grid. So let's say we have, a standard example. You're picking a number from 0 to 1. You pick another number from 0 to 1. To basically do is you graph this on like a square, right? You have 0 to 1 on the x-axis and 0 to 1 on the y-axis. You're trying to say, okay, what is the probability that they at least differ by half? And because we're choosing any real number, there's infinitely many possibilities. You can't possibly do casework with this. The idea is now we have to look at geometrically because that will help us deal with the infinite possibilities. Because it's very hard to deal with that. You can use calculus and whatnot, I'm sure, but geometric probability is kind of graphing it is a way to go about it. It's a simple, intuitive way. So in this case, let's say we're trying to say the numbers have to differ by at most half. You would just be like, okay, if x is 0, y can be at most half. If x is half, then y can be anything. If x is 1, then y has to be at least 3/4. And doing so, we kind of can do this. We kind of bound out a region like this. And take a look here. And now the probability is just the area of this region divided by the total area of the square. A very common trick. And sometimes there's like trickier cases where you have to do geometric probability multiple times. And sometimes even on the recent AMC, geometric probability in 3D. There's this question about, okay, what's the probability that x plus y plus z is going to be less than or equal to 1? And in that case, you would just use tetrahedron volume formula because x plus y plus z equals 1 is a tetrahedron. So in that case, it would just be 1/6 because of half. If you have let's just write this out. Let's say you're trying to find the probability that this is true, where x, y, and z all are between 0 and 1. They're just any real number. So you could do this in 3D. You could be like, say this here, and see the equation of the plane is just going to pass through these points. The volume of this tetrahedron, 1/3 height, which is 1, and base area, which is half times 1 times 1, half. So just 1/6 is the answer. Yeah, and this actually came on the AMCs recently. Okay, now expected value is just kind of like a weighted average, and I've got a simple example here. Expected value of a dice roll okay, there's a 1/6 chance of it being 1, a 1/6 chance 2, all the way till 1/6 chance of 6. Our expected value, just the sum of that. You multiply the probability times the outcome. And you do that for all of your values, and you get the expected value. And it's a quite common topic. And here's where it's like a very, very useful thing. It's called linearity of expectation. What it says is if you've got a bunch of events happening, it doesn't matter whether they're dependent, independent, whatnot. You can just find the expected value that each one is going to happen. So let's say you have this number, and you're saying that it's like a number, let's say you're saying, and you say, this number is going to be, this value is going to vary between 0 and 5. Or let's say it's going to be some number between 1 and 5. This number is going to be something between 3 and 9. This number is going to be something between 4 and 7. What is the expected value of this number? You could just say, okay, what's the expected value of this hundredths digit? That's just 4 plus 7 divided by 2, 5.5. The expected value of the tenths digit, 3 plus 9 divided by 2. That's just 6. The expected value of the ones digit, 1 plus 5 over 2, 3. So you would just be like, okay, 100 times 5.5 plus 10 times 6 plus 1 times 3. And you would just add this up. So the idea here is that you can treat, when you're trying to find the expected value of many things, like you can break it up into individual components. You just find the expected value of each component. It's very easy to just add up and be like, here's your expected value. And even if, let's say, here's another slightly trickier example. Let's say we have a 2-digit number, and this value is anything between 1 and 9, and this number is going to be anything that's at least as big as the first digit. So you see how it's now dependent. It doesn't matter. We still can use linearity of expectation. The final digit can be 5, is on average 5, correct? And the tens digit, well, we can just say find the average value of this tens digit across all possibilities. And to do that, we just like, okay, the average value of the ones digit is 5, so the tens digit has to be at least 5, or on average, it's going to be at least 5 and at most 9. So on average, it's just going to be 7. So you would just be like, okay, 75 is our answer. The 7 is the expected value for the tens digit, and 5 is the expected value for the ones digit. You see how we can just, even though this was dependent on this, we can just use the expected value of this as our parameter. We don't have to consider every single case. Okay, when this is 1, this is from 1 to 9. So the expected value is 4.5. When this is 2, the expected value is now 5. When this is 3, we can just literally treat this as, okay, this is expected to be 5. That means this thing is going to be expected to be between the average of 5 and 9 divided by 2. It's a really cool trick. And I covered this in more detail in the series if you're confused. I went over it super briefly here. Okay, so here's a really cool example using linearity of expectation. Let's say we have 8 people, and between any 2 of them, there's a half chance that they're friends. So there's a half chance these 2 people are friends, half chance these 2 people are friends, so on. The question is, what's the expected number of 3 people, groups of 3 people, such that they're all friends with each other? So this is a classic example of linearity of expectation. So rather than being like, oh, there's 8 people and trying to do some complicated stuff, focus on just 3 people. Let's just talk about these 3 people. What's the probability they're all friends? There's a 1/2 probability these 2 people are friends. There's a half probability these 2 people are friends. And a half probability these 2 people are friends. So there's a 1/8 probability all 3 of them are friends. But this is not just true for these 3 people, but for every 3 people. So the expected number of, if you just have 3 people, the expected number of such friend groups of 3 people is 1/8. But we have 8 people. So we have 8 choose 3 possible triplets of people. And only 1/8 of them result in all 3 of them being friends with each other. So the answer is just 8 choose 3 times 1/8, which is 56 divided by 8, or 7. Okay, now recursion. And recursion is a process of solving for small values and then writing a recursive equation. You're going up. And a very standard example of this is, let's say you have a stair with like a bunch of stairs on it, a bunch of steps. And you're trying to find how many ways can the person go from the bottom stair to the, let's say, 7th stair. So the thing is basically you just, let's say, rather than solving it for 7 directly using some bashy casework stuff, we just use recursion, which is like, okay, if we're trying to find the number of ways to go to the first and second square, that's pretty easy. But now if we're trying to find for the seventh square, it's not easy. So what we're going to say is, using the previous values, we're going to write a recursive equation. Okay, so let's say in this problem, the person standing can either go one step up or 3 steps up. So the logic here is we just say f of n, well, for all the ways the person is 1 step below, so f of n minus 1, plus all the ways the person is 3 steps below, f of n minus 3. And then we just use this equation along with their small values of f of 1 and f of 2, and we can just work our way up. We can make a table. We can just be like, okay, f of 1 and 2 we did manually, and now 3 we just use our formula, and then 4, and then 5, and then 6, and then 7 until we're done. So pretty cool trick. And again, I covered this in more detail. And now we're going to talk about probability states, which is, I think, our last topic. And to do this, rather than reading a very boring instruction manual, let me just show you an example. Let's say we have this state A, which is, let's say, and then we have this state B. So what we're trying to say is, let's say there's 2 players. Let's say it's player A and player B. And let's say we're trying to find the probability player A wins the game. So you can be like, okay, on any given turn, there's a 2/3, let's say it's A's turn. We're trying to find the probability A wins. Let's say there's a 1/3 chance A will win the game. The 1/3 chance is just a win. So what we're doing is we're drawing like a Markov chain, is it what it's called. And then there's a 2/3 chance A does not win and it becomes B's turn. Okay, so now player B. Player B, now let's say, is better than player A. So let's say player B has a 2/3 chance of winning. So what we do is we draw a state, and you can be like, okay, B win. And let's just say A win here, and B win. Let's say 2/3 chance, and then if not, it goes back to A's turn, so 1/3 chance. So now we're trying to be like, okay, this is an infinite process. We cannot just do this for like a few small values. What we do is we write states equations. So we're like, okay, if it's A's turn, the probability of winning is, okay, there's a 1/3 chance of just winning right on the spot. But there's also a chance, it might go to B and then it comes back to A's turn and A might win. So there's a 2/3 chance that A will win. There's a 2/3 chance that it will go to B's turn. Okay, so now what we're going to do is say, let's say the probability of A winning when it's B's turn is P of B. So P of B is the probability that A wins when it's B's turn. So then we're like, okay, P of B. Now what is P of B? P of B, well, there's a 2/3 chance that A will definitely not win if B wins. And then there's a 1/3 chance it goes back to A's turn. So what's the probability of it winning if it's A's turn? P of A. You see how now we have a 2-variable equation with two equations? So it's really neat. We can just solve it, and we can find the probability of winning if it's A's turn for A, and the probability of winning for A if it's B's turn. Okay, so now let's slightly modify this. Okay, let's just say that it never goes back here. I don't know. Let's just say we have from B. Let's say that A is guaranteed to win. Let's say, okay, or let's take a different example maybe for expected value states. So let's say we have a person who's trying to reach the end of the tower. Let's say I don't know. I just took a random example. So let's say they're 3 steps away. So you can be like, okay, 3 steps away, and then 2 steps away, and then 1 step away, and then finish line. So let's say that there's like a number line, let's say there's like a bunch of points, right? So let's say this is our finish line over here. And this is, let's say, our boundary. You can't really go beyond it. Or yeah, let's just say there's nothing here. But we're on this line. We're trying to reach the finish line, finish. And we start at this point over here. So let's say that from 3 steps, there's a guarantee you go to 2 steps away. From 2 steps, there's a half chance you become 1 step away. but there's also a half chance you go back to being 3 steps away. When you're 1 step away, there's a half chance you go to being 2 steps away, and a half chance you go to finishing, let's say. So on every turn, as long as you're not at the beginning, there's a half chance you go back or forth. And then there's a half chance of finishing. So notice here, you just keep moving back and forth. It's guaranteed that eventually you're going to reach the finish line. After how many moves, we don't know. But eventually you're going to keep moving back and forth. You're eventually just going to get lucky enough to reach the finish line. So let's just try to find the expected number of moves for this to happen. We do something very similar here, except we're going to write an expected value states equation. So we see the expected value from 3 steps away, let's say, is e of 3. The expected number of steps it's going to take from 2 steps away is, let's say, e of 2. And from 1 step away, let's call it e of 1. And and from 0 steps away, it's just going to be 0, of course. E of 0 is just obviously going to be equal to 0. Because when you're already at the finish line, the expected number of additional steps is 0. So what we're trying to find is e of 3. From point 3, how many expected steps are we going to take? So what we can do is write these equations. From 3, there's a half chance, or there's a guaranteed chance of going to 2 steps away. So do we just say e of 3 equals 1 times e of 2, like we did for probability? No. It's slightly different here. Let's say the number of expected steps from getting from 2 steps away is x. The number from 3 steps away, it's not going to be x. Remember, we took 1 step to get to this point. This whole process of going from here to here was 1 step. So what we have to do is add 1 in this equation. Similarly, we would do something for e of 2. Let's say there's a half chance of going back to e of 3 and a half chance to going e to 1. But there's also one additional step. This process of going to e of 3 or e of 1 takes one additional step. So the expected value at position 2 is 1 more than this. And then e of 1, same exact thing. Half e2 plus half, 1 finish line, which is just 0, because expected value from the finish line, expected number of more steps from the finish line is 0. And then we add 1. And now take a look. 3 variables, 3 equations. It's not hard to solve at all. I'm sure you can do this on your own. So yeah, that's the idea here. Always add 1 for each step you take. And for states, you don't need to do that because it's just probabilities. And that's it for combo. Now we're moving on to algebra. So here are some basic exponent rules, which I'm sure you guys all know. So let's move on to binomial square expansions. X plus y squared equals x squared plus 2x plus y squared. And you probably know this, but it's very important to notice when to look out for this pattern. It's not always going to be this apparent. Sometimes it's a little bit hidden. And another very common trick is it's equal to x minus y squared plus 4xy. When we get to Vietas, you'll see that, let's say we know x plus y and xy. And you're trying to find x minus y. How would you do that? Well, you just plug it in here. You take your value of x plus y, and then you take your value of xy, and then you see, okay, x minus y, you can get it pretty easily from this equation. From Vietas, you know, when you know these two values, you can easily find this. That's why this is super important. This is basically the same thing using this factorization here. And yeah, these are just some alternative variations of this where you add them together. The two xy's cancel. That's sometimes useful. When you subtract them, the x squared and the y squareds cancel. And then we have this factorization here, which is x squared plus x plus y plus z squared is x squared plus y squared plus z squared plus 2xy plus yz plus xz. Okay, now binomial cube expansions. X plus y cubed equals x cubed plus 3xy times x plus y cubed. Basically, it's this thing. And for minus y cubed, it's the same thing, except now it's minus, you kind of alternate signs. X cubed, then minus 3x squared y, and then plus 3xy squared, and then minus y cubed. Yeah, and then this is just factoring this, combining it all into one term. And then we have this expansion, which is super useful, probably the least known. It's useful because when you have to find this quantity here, it's very easy with this factorization. X cubed plus y cubed plus z cubed minus 3xyz is x plus y plus z times x squared plus y squared plus z squared minus this pairwise sum. A super cool factorization. Definitely going to need it, especially when we're using Vietas and we're trying to find, let's say, like r cubed plus s cubed plus t cubed with the roots. this factorization is often used for that. So yeah, that's pretty much it for this slide. Oh yeah, but let me just, and then bring about some other factorization that's not here. So yeah, Simon's favorite factoring, that should be there, yeah. Okay, we'll talk about that later, maybe. Okay, so we have this cool little thing here, where x plus 1 over x is a, then you have x squared plus 1 over x squared is a squared minus 2. Why? It's very simple. You just do this squared, you get x squared plus 1 over x squared, but then you also get a 2x times 1 over x term along with that. So that's where that 2 comes from. And then x cubed, we just do something very similar. Well, you can just do x plus 1 over x cubed. And then we see that there's a 3 times, there's gonna be like a 3 x times x 1 over x, and then x plus 1 over x term here, and then this stuff cancel, and this is just a, right? So that's where this comes from. And for fourth, you just do the same thing you did for square, except now you're dealing with x squared as your base. So now it just becomes this squared minus 2. You see how it's basically like the same thing as this, except now we're using our value of here to get here. Okay, now this difference of squares, you probably know. Difference of cubes, x cubed minus y cubed is x minus y times x squared plus xy plus y squared. And sum of cubes, just the key thing to remember here is these signs always match, and then these signs are always opposite. That's how I never get confused. These sides match, and then these sides are opposite. Yeah, x cubed plus y cubed is x plus y, and then x squared minus xy plus y squared. And higher power factorizations, so for example, this looks scary, but for example, we have x to the 5 minus y to the 5. It's just x minus y. And then now we just be like, okay, x to the 4 plus x to the 4, x to the x cubed y plus x squared y squared plus x y cubed plus y to the 4th. It's just every single 4 term with 4 variables multiplied. We have this. We have this quantity here. And this is true for any number, not just 5. You know, you can see the general form here, just basically the same thing we wrote out for 5. And for only odd powers, you can also have the sum factorization. So for example, x to the 7 plus y to the 7 is x plus y, and then times x to the 6, and then minus x to the 5 plus x, or whoops, I did not. Always the degree of every term in this is going to be 6. So minus x to the 5y plus x to the 4y squared, and then you just keep alternating signs, and then you keep, like, you know how we see 6, x to the 6, x to the 5, x to the 4, all the way till, all the way till you get to y to the 6th. You just keep alternating signs, and you keep reducing the value of the x exponent and increasing of the y exponent, and you alternate signs. And this only works for odd. Be very, very, very careful here. Yeah, and then Simon's favorite factoring trick, you know, it's super useful in these types of scenarios when you get xy plus 3x plus 3y, and then you're trying to be like, okay, find all integer values such that this is equal to 20. You know, if you did AMC, you know these types of questions, or math counts, you know, these very standard types of questions. And oftentimes they'll disguise it, and they'll be like, okay, find the sum of all possible pairs of two numbers such that the sum of the fractions is half, and really, you expand it out, it just becomes Simon's favorite factoring trick. And yeah, something cool is that, let's say we have 1 here. We just get xy plus x plus y plus 1, right? That's pretty simple. But now what if we do extend that for 3? Kind of a generalization we're doing here. Take a look. This is xyz plus xy plus yz plus xz. And then plus again, x plus y plus z plus 1. If you, oops, I didn't show that earlier. If you ever get to the VNS chapter and you're wondering and you're confused and you're like, let's say a question asks you, what is the sum of the product, the pairwise, and the sum? And you can just use this oftentimes, and that's a pretty cool trick you can do there. So now, yeah, algebraic equations, these are, you know, seems like, you know, the simple linear equations you do in school, but the ones in AMCs are much trickier and much more interesting as well. So yeah, sometimes we have our similar techniques, substitution, elimination. You know, it's not always going to be in the standard linear equation form, but you know, when you have more complicated equations, these same simple techniques still apply. Sometimes you have to add, subtract, multiply equations, especially when you want to get rid of terms, group terms together, common denominator. You want to get rid of things, you want to get rid of fractions whenever possible. And then here, kind of, the factorizations we discussed are often useful. And then these two are kind of like the ones which people have the most trouble with and the most tricky, using symmetry and making smart substitutions. There's this, here's this like really cool problem from the AMC or something. I don't remember exactly where it was from. Yeah, it was something like this. It was like x equals xyz minus 3, y equals, or yeah, let's just do the simpler version. Let's say we have x equals xy minus 1, y equals xy plus 3, and now we're trying to solve this. So the thing here is, by multiplying equations, we basically combine our variables. So it's kind of a cool trick. We multiply, we get xy minus 1, xy plus 3. So now it's like by multiplying, even though we originally had two variables and now we only have, or two equations, and now we'll only have one equation, we've also made it just one variable. So that's a cool thing to keep in mind here. And yeah, the symmetry. So there's this another problem where it's like, okay, 1 minus x, don't remember exactly what it was. Or yeah, there's a problem I did in the mastering series earlier where we have, for example, like a plus 5 over b plus 7. And then b plus 3 over b plus 11. And then over here we have ab plus 5b plus 3a plus 15 over something like this. Over let's just say ab. I don't know exactly what it was, but the point here is that when you see these recurring themes and you're like, this is just a plus 5 times b plus 3, you question, like, is it really better to work with an a and b? Or is it maybe good to consider a substitution? Okay, let's just say that this was something else. This was ab plus 3a plus b. So when you're dealing with something like this, yeah, let's just something like this, right? You see that, okay, a plus 5, b plus 3. And this thingy over here is just a plus 5 times b plus 3. So this motivates a variable shift. So you're making like kind of smart substitutions that can simplify your expression, right? Let's just make this thingy, let's say a naught, and this thingy b naught. So now we have a much simpler equation. Let's write this, b naught over b naught plus 8. And then now we have a naught, b naught over something. I don't know what it is, but it doesn't really matter. The purpose is this substitution now made our things much simpler to deal with. Okay, and like symmetry between variables. So for example, there's one thing here. Yeah, there was the problem earlier where you have something like 1 minus x plus 3 and then plus 1 minus x minus 7. And then you have something. I'm just trying to show strategies here. I'm not going to go through full examples or anything. So the idea here is you consider a substitution, y equals x minus 5, and this allows you to use a symmetry. But let's take a look. These two things are symmetric about x minus 5. So this makes it much easier because now we have 1 minus y over 2 plus 1 minus 1 over y plus 2, or oops, I flipped that around, equals this. So I don't know whatever this was, it doesn't really matter. But the point is now, when we cross multiply, our expression is much easier. Take a look. When we cross multiply, we now get y minus 2 plus y plus 2 over y plus 2 times y minus 2. That's just difference of squares. And this is just 2y. So you see, if you just directly combine it here, it would be a little bit ugly. 2x minus 10 over x squared minus 10x plus 21. That's a little bit ugly. Versus this substitution, we use the symmetry. It's symmetric about x minus 5. So let's just say y is x minus 5. And then we get this really nice symmetry. Yeah, and then also looking for common factorizations. We discussed those in the previous page. Yeah, quadratic formula, just negative b plus or minus square root of b squared minus 4ac over 2a. You're probably familiar with that from school and stuff. So yeah, the discriminant of the quadratic, if it's 0, then the quadratic has a double or repeated root. If it's positive, it has two different real roots. And if it's negative, it has no real roots or two complex roots. Okay, so Vieta's formulas, these are so useful. I cannot stress the importance of these. So the sum of the roots, if you have a quadratic, you just take negative of this and then divide that by a. That's the sum of the roots, and roots is just the values that make this equation 0, the solutions of x. The products of the roots is you just take c and divide by a. So you see how we start off with negative here and then go to positive. And for example, let's say we have x squared, 2x squared minus 3x plus 7. We're trying to find the sum of the roots is just going to be, well, let's just write our negative, positive. Sum of the roots is negative of this coefficient divided by 2, 3/2. The product of the roots is this coefficient divided by, we always divide by this a coefficient, which is just 7/2. So we start off at negative for the sum, and then you just alternate. And for higher degree polynomials, it's very similar. You can find the general form here, but this is quite scary. So I like to just take simple examples to explain it more intuitively. So let's see if you have this random cubic, right? So we do a very similar thing with two variable Vietas. We start off here, and here's what I like to do. Negative, positive, negative. Right? So what we just say is sum of all three roots this time is negative of -7 by 2. And what is the second term here? And the second term is going to be the sum of the pairwise roots. So let's say our roots are r, s, and t. This would be rs plus rt plus st. That's pairwise sum would be 5/2. The product of the roots, which is rst, would be negative, right? Because you see a negative sign on top. We always start at negative over here and then alternate. Is going to be -6/2, which is -3. So as this alternating thing, make sure you remember the sign configurations. Yeah, and then RST. So in general, this is not just true for cubics, it's true in general. So you just start for the sum, which is like the sum of, you can think of the sum of the products of every one root. And then the next is the sum of the products of two roots, all those sums of all the products of two different roots. And the next is if you have the sums of the products of three different roots. And then finally, just the product of all of the roots. You know, that's the last term here. Product of all n roots, and this always alternates. That's why you get this -1 to the n. So yeah, so Vieta is just a formula, and they're never going to ask you in AMC to find the sum of the roots. That's too easy. They're going to give you these kind of root expressions, like for example, 1/r plus 1/s plus 1/t. And in this case, it's about noticing, how can I use Vietas to find this? In this case, notice that this is just rs plus st plus rt over rst. And even this is quite simple. There's going to be much more complicated ones. Like, for example, you could be 1/r minus 3 cubed, and then you could be etc. for a cubic. And that would be, that's much more difficult, right? You can still sometimes do it with Vietas, smart, clever algebraic manipulation. You clear your denominators, you add stuff up, you expand, and then you group stuff together. And another cool trick to remember is, if you have r plus s plus t, you can always find r squared plus s squared plus t squared just by squaring this and then subtracting 2 of this from our factorizations earlier. And that's why they're so useful. So yeah, so Vietas itself, it's never going to be like, oh yeah, sum of the roots. They'll often be like, okay, use this manipulation here, or use this manipulation here. And all these different manipulations using what you do know in order to find some other given quantity in terms of the roots. You might be like, why don't I just find the roots and then just plug it in? Because finding the roots is not going to be that simple. Okay, now polynomial root representation. So when we're doing polynomial problems, there's generally two strategies you can use. You can say your polynomials of the form ax, let's say cubed plus bx squared plus cx plus d. That's one form. Another form for your polynomial is you can be like, it's a of n, which is a leading coefficient of this, times x minus r1 times x minus r2, or so on, where these are all the roots of the polynomial. So oftentimes you have to be like, which representation is easier for me? Oftentimes this representation results in many useful properties that when you just express it like this, you miss out on. So the key thing is when it's a monic polynomial, it's just x minus the product of all the roots. Pretty cool. So yeah, this is a really cool trick. Let's say a problem is saying you have this cubic. Let's just go to the previous page. And you're trying to find 3 minus r, 3 minus s, times 3 minus t. Let's say. So one way to do this is to expand this all out, 27, and then minus 3 RS plus RT plus ST, and then plus RST. You know, that would work, and then you can plug in your Vieta stuff. But there's a really neat trick. And the thing is using the polynomial representation of a root. Notice that this thingy is just equal to 2 times x minus r, x minus s, x minus t. So if you want to find this thing for 3, we just plug in 3 to our polynomial. And then we get this, but instead of x, now it's 2 times 3 minus r, 3 minus s, 3 minus t. And if we're trying to find this, we just divide by 2 from there. That's kind of an example of how this representation is oftentimes very useful. So yeah, fundamental theorem of algebra, a polynomial of degree n has n roots always, complex roots, including multiplicity, which is like a repeated root. And remainder theorem, super important and useful. If you have some polynomial, I don't know, x cubed plus 2x squared plus x minus 7. The remainder, when it's divided by, let's say, x plus 4, it's very simple. If you're trying to do this, you just plug in p, you just find the polynomial evaluated at -4. Right? Whenever it's divided by x minus r, the remainder is just p of r. You just plug in r. But be careful, it's the opposite sign. So if this was x plus r, you would plug in p of -r. Don't want to mess that up. Yeah, and factor theorem, which is kind of a corollary. If something is the root of it, then we have p of r is 0, which intuitively makes sense, right? Because that's why these are all part of the polynomial. Because this happens, it's a factor, x minus r is a factor only when r is a root, or p of r is 0. Okay, so now we've got this really cool trick, which I'm guessing most of you will not know. And it's symmetric polynomials trick. And it's really, really cool. And it's useful when you have symmetric polynomials of even degree. So what do I mean by that? Let's say you have this thingy like something like this, right? Let's say you're trying to find the roots of this symmetric polynomial. And this is just a random example I just pulled. Notice how it's symmetric. 1, 1, 3, whoops, that is not intentional. Let's just make this 1. 1, 1, 1, 1, 2, 2, and then 1, right? So you see how it's symmetric and has to be of even degree for this trick to work. There's a really neat trick to do this. The thing is, first, check, which will not happen if you have a symmetric polynomial. X equals 0 is not going to be a root, clearly because of this, right? You plug in 0, you get 1 equals 0, not true. So you can divide out by x freely. So what we're going to do is take, because this is degree 6, we divide out by x cubed. This gives us x cubed plus x squared plus 2x plus 1 plus 2 times 1 over x plus 1 over x squared plus 1 over x cubed. We already know it's equal to 0, so don't worry about that. So now take a look at this. X cubed plus 1 over x cubed. X squared plus 1 over x squared. 2 times x plus 1 over x and 1. Does this remind you of anything? Remember this stuff from earlier? We covered it earlier. Don't remember exactly where, but right here, yeah. We can use these things, which you don't have to memorize. You can derive on the spot. But for now, if you want, you can refer back to this point in the video if you need it. By using these, take a look. Let's just call x plus 1 over x y. Now we can rewrite this as x cubed plus 1 over x cubed, which is just y cubed minus 3a. X squared plus 1 over x squared, which is nothing but y squared minus 2. X plus 1 over x, which is just y, so plus 2 times that, so y, plus 1. Take a look. Now we basically halved our degree of this polynomial. Instead of a 6-degree polynomial, we now have a cubic. And I don't know why I said a there when I have y everywhere else. So yeah. So now we have a cubic, which is much easier to solve than this. And later we can just solve, once we have y, we can just solve for x from here. So a really neat trick to keep in mind here. It's really useful when you have symmetric polynomials. It's a really cool thing in my opinion. Okay, now polynomial manipulations. Another super cool thing. We got a few more things left for algebra. Polynomial manipulations. So let's say you have this polynomial here. And you're trying to find, let's just use a quadratic. Let's say this is our polynomial. Now let's say we're trying to find a new polynomial that has all its roots that are reciprocals of the roots of the original polynomial. In this case, it's a quadratic, but it doesn't have to be a quadratic. So there's a really cool thing. So, let's just take this. So this thingy has roots 3 and 4, just by factoring. Now, what if we want to construct a polynomial 1/3 and 1/4? Now, in this case, it's easy. You just do x minus 1/3 times x minus 1/4. But in this case, you won't always just know these roots right off the bat. So what you can instead do is something cool. So notice that let's see, we factor this out, right? In this case, it's easy to factor, but let's just call it, we won't always be able to factor it this easily. So let's just say R and S for now. So actually, instead, so if you're trying to find something with roots 1 over R and 1 over S, what we do is we just replace x with 1 over x. So now consider this new polynomial, which is not really a polynomial actually, but we can make it a polynomial. Consider this. Take a look. If R and S are roots of this quadratic, then for this quadratic, 1 over x equals R. Now x is 1 over R. So if R and S are roots of this quadratic, now we have that 1 over R is going to be a root of this quadratic. Similarly, because if you plug in 1 over R here, we just get R squared minus 7R plus 12, which is 0 from this. So take a look. This new polynomial has roots 1 over R and 1 over S. And it's not yet a polynomial, but we can just multiply by x squared and make it a polynomial. So this becomes 12x squared minus 7x, 1. Take a look. It's the same as this polynomial, except, we can just rewrite this in a more standard notation. It's the same polynomial, except these things are flipped. So you flip the coefficients to get a polynomial with 1 over reciprocal roots. Yeah, and here's another cool polynomial manipulation, which is kind of a similar logic. Let's take our same polynomial just for demonstration purposes. We have this. Let's say we're trying to find a new, or let's just take any general quadratic, just for demonstration. It can be any polynomial, not just a quadratic. Let's say we're trying to find a new polynomial with roots r plus 2 and s plus 2. How would we do this? We would just simply put x minus r plus 2 and x minus s plus 2. But the thing is, we don't know what r and s are, so we cannot just, let's say this is just some random quadratic we can't easily find the roots of. I know you can use quadratic formula, but let's say you can't, because once you get to this, it's not just going to be that simple. How are we going to find a new polynomial that has roots that are each 2 bigger? And the trick is, you just plug in x minus 2 instead of x. So our new polynomial with roots that are 2 bigger is just this. Why? Because let's say r is the root of this. Now, we put in r plus 2 here. Now we get r squared plus 7r plus 10. And because r is the root of this is equal to 0. So you see how, because we put in x minus 2 squared, x minus 2 for all x's, now our roots are 2 bigger. And this is a really neat trick to keep in mind. And I cover all of these things. I have a whole video on this kind of stuff, polynomial manipulations. I cover with examples, everything. You don't want to just check it out in detail. You want to check out the Mastering AMC 1012 playlist in the description. So why is this useful? Because let's say we're trying to evaluate something like, 1 over r, let's say a simple example, something like this. How do we do that? I mean, you can use VNS, it's not hard. Or you can do a polynomial manipulation and then just directly use VNS to find the sum of the roots. But this is kind of a silly example because it's not hard with VNS. Now, what if it's something more complicated like this? So just for the sake of demonstration, let's use this quadratic. Again, it doesn't really matter. And let's say it has roots r, s, and t. So if you're trying to find this, you can just directly use VNS. You can expand it. It's going to be nasty. Not fun at all. So we're going to do this with a few polynomial manipulations. To start off, we're going to find a new polynomial which instead has roots r minus 3, s minus 3, and t minus 3. And this is pretty simple. We just plug in x plus 3 over here. And this gives us our new polynomial, which has roots that are all 3 smaller. And take a look at this. Now, from this new polynomial, all we have to find is, let's just say our new roots are capital R, capital S, and capital T. Now, from our new polynomial, all we have to do is find this, which is already so much simpler than this, right? But can we make it even simpler? What we're going to do is we're going to use the flipped coefficients trick. So let's just say you expanded this out and you got something, I'm not going to actually do it, but I'm just going to assume it's this random polynomial for now. It's not going to be this, but just say it is. It's not going to be this, but let's say we expanded it out and we got this, just for the sake of demonstration here. And this polynomial has roots this, right? So we could just be like, from this new polynomial, find 1 over this thingy cubed plus 1 over s cubed plus 1 over t cubed. But that's still a little bit hard. So we go one step further, we use the reciprocal root trick. We just flip the coefficients around. We just flip the coefficients around. It's that simple. Plus 7x minus 7x squared, and then plus 1. So now this new polynomial has roots 1 over r minus 3, 1 over s minus 3, 1 over t minus 3. And let's just say they're also x, y, and z. So take a look. From our new polynomial, now this expression is just x cubed plus y cubed plus z cubed, which is 10 times simpler to do than this. So now how would you finish with this? Well, remember this factorization from earlier? Yeah, that's super useful. You would just plug it in here. You can know the value of this. You know the value of this, it's just Vietas. And this you can also find pretty easily using Vietas, because it's just a plus b plus c squared. And then you subtract 3 times ab plus bc plus ac. Again, we're knowing the factorizations is immensely useful. Okay, so now we're going to take a look at Newton's sums. And this is a very advanced concept, but let's explore it regardless. So yeah, and I'm not going to explain this giant mess here, so I'm just going to use the space here to explain. So let's just take a sample polynomial. I don't know why I like this cubic so much. I just keep using the same polynomial. So Vietas will tell us that x plus y, or r plus s plus t for the roots is 7. Now, what if we wanted to find this? We could still do this with Vietas, right? It would just be this squared minus 2 times this. Now, what if we wanted to find cubed? We could use the T2's thing from earlier, right? We could do the whole factorization and then solve. But as you keep going, it just gets harder and harder. So it's like, maybe there's a generalization. Maybe there's a way we can do this faster using this trick called Newton's sums. And let's just explain what it really means here. And what we're going to do is we're just going to write a series of equations, and then they're going to be pretty easy to solve at the end. So what we're going to say is s of 1 is just the sum of the roots, right? S of 2 is the sum of the squares of the roots, and so on. S of 3 is the sum of the cubes of the roots, and etc., etc. So we have this, we can write our Newton's sums equations are. What we do is we look at the coefficients of this polynomial. So let's just write it out. We have 1 times, so we just take this first coefficient and we put s of 1 here. And then minus 7 equals 0. Always equal to 0. And this intuitively, makes sense, right? This is just Vietas, basics. Right? S1 is 7 just by Vietas. But this is like the first step in Newton's sums. Now this is where it becomes distinct from Vietas. Now next we write 1 S2 and then minus 7 S1. And then now what we do is we do plus 10, but then we multiply by 2. Why 2? Because that's this thingy. We put 2 here. So you can think of it like, we're supposed to have an S of 0 here, but instead of S of 0, we just put this here, 2 instead. we just put the coefficient or the starting value for our equation here, in this case 2. And we can keep going with this. 1 S3 minus 7 S2 plus 10 S1. Now we're at 0, so we just do minus 37. But instead of S of 0, we put this. Oops, we put this thingy here, which we started with. So times 3 equals 0. So you see here how we can just solve for S1. And then from that, we can solve for S2 from this second equation. And from that, we can solve for S3 from this equation. And let's just go one step further just to hopefully be clear on this. 1 S4 minus 7 S3 plus 10 S2 and then minus 37 S1. Uh-oh, we're supposed to have one more term, but there's no more coefficients of the polynomial. Then we just stop. We don't have to worry about, doing whatever. We just stop there. And similarly, if we're trying to find S5, we would do the same thing. We would just stop prematurely, and it's okay to do that. We don't have S1, that's perfectly fine. And this is a really powerful technique on the AME as well. It's a very advanced AMC technique, but it's still good to know if you're especially aiming to solve some of those last problems. So yeah, so here's some, especially compared to the stuff we've been doing, this is going to feel like very easy. You probably already know this stuff. AN is the first term times n minus 1 times d, and an arithmetic sequence. And in terms of AM, we just add n minus n times d. Number of terms, you just subtract last term minus first term divided by common difference, and then you add 1. Never forget this. Going through this quickly because I'm sure you guys know. The average term, just the first and the last divided by 2. The sum is just the average times n. And we can plug in our value of a of n earlier to get this formula, but you don't need to use this formula. You can literally just find the first term, the last term, and then average them and multiply. The geometric sequences, again, you probably know this stuff. Yeah, in general, g of n, in terms of g of n, we just multiply by as many r's. And then the sum, this is something people sometimes get confused with. You have g1, g2, all the way till gn. The sum is just the first term times r to the n, which is the number of terms. Be careful. There's different ways of writing this, but the way it's written here, n is the number of terms. So r to the n minus 1 over r minus 1. Yeah, be very careful here. N is not like sometimes some other formulas you might see have n plus 1 and define their n differently. You want to be very careful about that using here, which one you're using here. And for an infinite geometric sequence, it's just the first term over 1 minus the ratio, but that only holds true if it's between -1 and 1. Because if it's otherwise, it's not going to converge. It's not going to approach a finite value. Like, for example, 1 plus 2 plus 4 plus 8. It's not going to equal something finite. Yeah, and here's some other cool shortcuts. The sum of the odd numbers, the sum of the first n odd numbers is n squared. Sum of the first n even numbers is n times n plus 1. And the sum of the squares, you got to know this stuff, n times n plus 1 times 2n plus 6 by 6. And the sum of the first n cubes, it's kind of interesting. This is equal to 1 plus 2 plus all the way till n squared, which is this. So it's kind of a cool little trick here. Okay, now telescoping. Now we're going to move on to telescoping and partial fraction decomposition. Okay, so for telescoping, see, there's some really simple examples, like, for example, 1/2 times 2/3 times 3/4, all the way till 99 over 100, where it's, it's very simple. You just cancel. You get 1 over 100. But there's some more complicated ones as well, specifically partial fraction decomposition. So for example, let's say you have 1 over 2 times 3, plus 1 over 3 times 4, plus all the way until 1 over 99 times 100. So what you could do is you could rewrite this cool little trick. This is 1/2 minus 1/3, and then this thingy can be rewritten like this. And then this thingy can be rewritten like this. And then so on. And then take a look. Cancel. We're left with 1/2 minus 1 over 100. That's it. So cool little trick there. And also sometimes, like, why is that true, really? And intuitively, the reason we do that is we decompose this. So we say this is equal to a over n plus b over n plus 1. Now our quest is to find what is a and b, so that this becomes, we're trying to decompose it. So what is the value of a and b? And yeah, to do this, you just multiply by n times n plus 1. You get you get 1 equals an plus 1 plus bn. And take a look. We can't have any n's in our final factor. So a is equal to negative b. And then finally we have that. So we also have a is equal to 1 as well, because, you know, this is the only thing there. Because there can't be any n's on this side. There has to be just 1 on this side. We can't have 2n plus 1, because n has to be true for all n. Right, so we just solve for here for a and b. We get, in this case, it's 1, negative 1. Another example where it might be good is like 3 times 5. In this case, it's like 1/2. It's half of 1/3 minus 1/5 by 2. Yeah, so pretty simple there. Now mean, median, mode. Mean is just the average of all the terms. Sum divided by number. Median is just the middle number. You know, if it's even number terms, you average the middle 2, and mode is the most common. Pretty simple stuff. It's never going to probably happen outside the first 15. Obviously, they're not going to be like, what is the mean of 3, 5, and 7 on the AMCs? But they might give you some tricky scenario like, okay, the difference between the mean and the median is 4. And the mode is 4 greater than the mean. What is the largest possible number in this set? Or something like that. Where you have to do a little bit of trickery and casework to sometimes figure stuff out. And some other types of means, harmonic means and quadratic means. And did I skip the rate and word section? I think I might have skipped some section about, oh, maybe we're covering that later. Never mind. Okay, yeah, work and rate. So yeah, work is rate times time, and this is kind of some pretty obvious stuff. And here's like a cool trick. Let's say there's a job. Someone can do it in 3 minutes, and the other can do it in 5. To find out how long they can do it together, you just have this neat formula. AB over A plus B. And the same thing works for like the pipes. If 2 faucets takes A and B hours to fill, again. Yeah, so this is pretty basic stuff. And for speed, again, remember average is total distance by total time, not just the average of the speeds. And sometimes with AMC, you have to do these word problems where you set up an equation, and sometimes it can be a little bit difficult too sometimes. So you shouldn't just brush this off as an easy topic. The tricky part is often figuring out what equations to write and how to write them. So just set up your speed, distance, time equations and solve them. That's the only strategy for these types of problems. I think most of you are comfortable with that. And now we're on to number theory. So starting off with the very basics, primes have 2 factors. We have all these numbers here, which are primes. Some really common tricks on the AMCs that occur. Number of factors of a number. You have this prime factorization. The number of factors, you just add 1 to all these exponents and multiply. For example, let's say we have 2 cubed times 3 squared. This thing, we have 3 plus 1 times 2 plus 1, which is 12 factors. And there's some other tricks for sum of factors. So for example, in the same example, 2 cubed times 3 squared. We just do 1 plus 2 squared plus 2 cubed. And then we multiply this by 1 plus 3 squared. Right, we look at 3 squared, 1, 3, and 3 squared. We look at 2 cubed, 1, 2, 2 squared, 2 cubed. And we just multiply that. Why is this true? You can imagine pairing it. This forms a factor. This forms another factor. This forms another factor. So if you expand this out, you'll get every single possible factor of this number. And that's why this is so powerful. And the product is also pretty simple. Again, for the same example, all you have to do is take this number, which is 72, and take it to the power of the number of factors, which is 12, divided by 2. So why is that true? Well, imagine you pair the numbers up. 172, 236. Every factor can be paired up. So for every 2 factors, we multiply by 72. So that's why it's just 72 to the 6th power in this case. And divisibility rules, I'm sure these ones you all know. In fact, for 7 and 11, 11 you guys know, but 7 and other obscure ones like 13, 14, the strategy I like to use is you just take away multiples of 7 until you reach something manageable. For example, 1100, you subtract 700, then maybe subtract 350, and then subtract 49. You're left with 1, so it's 1. Okay, now we're moving on to some actual stuff. So GCD LCM, which is, you guys know the definitions of, I'm sure. But there's this cool identity here. GCD of 2 numbers times the LCM of 2 numbers is just the product of the 2 numbers. This is super powerful. And similarly, another cool identity, if 2 numbers have a common factor C, then we can just factor it out of the GCD. That should be pretty intuitively obvious, right? we have something like this. To find this GCD, I mean, of course, 6 is a common factor. It's just going to be 6 times the GCD of 4 and 12. And now we have Euclidean algorithm, which is super useful for evaluating large GCDs. And I have this whole example written out here in this, so you can check this out. GCD of 186 and 92. So basically what you do is you subtract multiples of 92 from 186. Basically what Euclidean algorithm states is that GCD of 186 and 92 is the same as GCD of 186 minus 92 and 92. And that we can do this again. We can subtract 2 multiples of 92. And this gives us this. And now with this, we can just say, now we can do it in reverse, right? Because now this number is smaller than this. Now we can say GCD of 2 and 92 minus 2 times 46. So now we're subtracting multiples of 2 from 92. We get GCD of 2 and 0, which is just 2. Okay, now Bézout's identity. Basically, it's saying that let's say you have 6x plus 14y. What values can C be? Okay, so clearly it has to be even because this is even, and let's say x and y are integers. Clearly this has to be even, right? 6 is even and 14 is even. But there's actually a really cool identity that says that for every even number, we can always find an associated x and y value. And you can actually find this out using reverse Euclidean algorithm, but I think that's a bit beyond the scope of this video, so I'll leave it out for now. But if you're interested, let me know in the comments below. I can explain this if you'd like, but let's say you're trying to find the value of x and y in general, such that this thing is equal to 4. There's a whole reverse Euclidean algorithm process you can use to find it. Okay, now modular arithmetic, the heart and soul of number theory. If a number n is a mod b, it just leaves a remainder of a when divided by b. And this is pretty simple. If a is x mod n and b is y mod n, then ab is the same as xy mod n. Similarly, and this is just a generalization of this, right? If a is the same as x mod n, then we have this, which is just applying this repeatedly, right? So for example, let's say 37 is 2 mod 5. You're trying to find the value of 37 to the 10 mod 5. It's the same as finding the value of 2 to the 10 mod 5 because 2 and 37 are the same mod 5. And digit cycles, where this is kind of like, for example, let's say you're looking at the last 2 digits of 7 to the power of. So let's say we're trying to find 7 to the x mod 100. There's a really cool cycle here. 7 to the 1 is 7, congruent to 7 mod 100. 7 squared is congruent to 49 mod 100. 7 cubed is congruent to 43 mod 100. 7 to the 4 is congruent to 1 mod 100. And then 7 to the 5 goes back to 7 mod 100. You see how this kind of cycles? So let's say we're trying to find the value of 7 to the 137 mod 100. So the thing you don't want to do is say 7 times 7 is 49. And then just keep multiplying by 7 until you get to 139 powers. You can just use these handy cycle here. 7 to the 139 is the same as 7 to the 3 mod 100, which is just 43. Because we cycled every 4. So we just subtract off multiples of 4 from our exponent. And now we have Euler's-Tauschen function, which is useful in Euler's-Tauschen theorem and Fermat's little theorem. So for example, we have 2 to the power of 5 times 3 squared times 5 to the 7, let's say. To find the totient, you just multiply this number, then you multiply it, and you look at each of the primes. So let's say for prime 2, we multiply by 1 minus half. For the prime 3, we multiply by 1 minus third. For the prime 5, you multiply by 1 minus 1/5. And so on. So, eventually, this just gives us the totient of n. And yeah, first step, you have to find the prime factorization. I mean, that's kind of what you do in number theory. So Euler's-Tauschen theorem. Let's look at Fermat's little theorem first. What this is saying is 2 to the power of any number to the power of p minus 1, where p is a prime, is 1 mod p. For example, 2 to the 6 is 1 mod 7. So basically, every 6 values, this cycles and comes back to 1. We have 2, then 4, then 8, which is just, or 1, and then 2, and then 4, and then back to 1. So you see that 2 to the 6 is 1. And what this tells us is that, let's say we have 2 to the power of 47. This is just going to be the same as 2 to the power of 5 mod 7. Because we can, these things, 47 and 5, because it cycles every 6 exponents, 47 and 5 are the same mod 6. So these are going to be the same mod 7. And that allows us to make our things much easier often. And Euler's Totient theorem is just a generalization of this. And it works for n, not just p, but for any number n. For example, we have 2 to the power of quotient of 100, let's say, is 1 mod 100. Quotient of 100, well, this is just a standard process, 2 squared times 5 squared times 1 minus half times 1 minus 1/5. And I have a whole video on Euler's Totient on this channel. You can check that out. 4/5 times half times 100, which is going to be 40. So 2 to the 40 is 1 mod 100. And if you ever get lazy, you don't want to write mod in your paper over again. This is like something that not many people do, but I personally like to do in my own scratch work, where I just do this shorthand notation, 1, and then I just do bracket 100. Because I think, okay, mod is understood, of course, right? You can use that if you'd like, but if it's confusing, you know, this is just something, a personal preference. Okay, now modular inverses. So if you have a number a, let's say 2 mod 5, the inverse of the number is a number in mod 5 you can multiply by, now you get 1 mod 5. In this case, our inverse is 3 mod 5. Because look, 2 times 3 is 6, which is just 1 mod 5. So in other words, we could say 2 inverse is congruent to 3 mod 5. Okay, now Wilson's theorem. P minus 1 factorial is negative 1 mod p. And I probably forgot to mention this earlier, but having negative mods is okay. For example, negative 1 mod 7 is just the same as 6 mod 7 because 6 and negative 1 leave the same remainder when divided by 7. And what does Wilson's theorem say? It says that 7 minus 1 factorial is congruent to 7 minus, or just negative 1 mod 7, which is just 6 mod 7. A pretty cool thing. And the proof is also really neat, but again, outside the scope of AMCs. You can check it out in like probably some AME level or early Olympiad level textbooks if you're interested. Now, binomial theorem. And you might be like, why is this a number theory? So basically, it's like x plus y to the n. We have n choose 0 times x to the n y to the 0. N choose 1, x to the n minus 1 y. So on all the way till n choose n, x to the 0, y to the n. So let's say we're trying to find the value of 11 to the power of 100 mod, let's say 11 to the power of 30 mod 100. So now you could try and, Euler's Totient theorem won't help. 11 to the 40 is just, well, what? 1 mod 100. That doesn't help us at all, because now, and we don't want to manually multiply 11 30 times. That is, unless you want to spend the entire 75 minutes in the AMC contest doing that. So we have a neat little trick using binomial theorem. And this generally works when, let's say you're like having something 11 and then 100 here. So what we can do is say, make this 10 plus 1 to the 30 mod 100. Why is this useful? Because take a look at this. Now, let's just move that up. When we expand this using binomial theorem, every term except the last two are going to be multiples of 100. Right? We're going to have 10 to the 30 plus 10 to the 29 times 30 choose 1. So on, all the way until 10 to the 1 times 10 to the 1 times 1 to the 29 times 30 choose 1, and then plus 1 to the 30. Take a look at this. Every term from here all the way till here have a 10 squared factor in them. So they're all 0 mod 100. We just care about these last two terms. But even this term, 10 and then 30 is a multiple of 10. even this term is 0 mod 10 in this case. It might not always be. So in this case, we get an answer of 1. Pretty neat thing with binomial theorem here, how we used it to eliminate all those extraneous powers 100. When is this useful? It's useful when you have something of the form, let's say like a to the power of something mod 49, right? Because now we have a little bit more than 7, and we're dealing with 7 squared here. Or it could also work for 6 to the power of something mod 49. Same thing, except we would do 7 minus 1 to the power of whatever. This is not a 0. This is just some blank value, which can be anything. So super powerful thing to keep in mind as an alternative. And there's something I forgot to mention on this previous slide, which I probably should. Sometimes this is super weak. Like it's not, for example, in this example, as you can see, it actually cycled after 3. And this is actually known as the order, which is, again, beyond the scope of AMCs. But the point is that it's not always going to be the case that it takes 6 values to go back to 1. Sometimes it might come home to 1 early. And so sometimes if you can, for example, just over here, the Cauchy theorem, oftentimes there's a much easier variation using Fermat's theorem and Chinese remainder theorem, which we'll just talk about over here. So basically what Chinese remainder theorem says is if you have x equals a bunch of values mod different things, n1 through nk, there's a unique solution mod their product, as long as these are all relatively prime. For example, let's say we have x is 5 mod 8 and x is 2 mod 5. There's going to be a unique solution which we can find mod 40. And in this case, I think it will turn out to be, what? 37. But let's say it was something like this. X equals 5 mod 8, and then x equals 4 mod 6. Take a look. This doesn't have a solution because these things are not relatively prime. So Chinese remainder theorem does not guarantee a solution mod 48 because these things are not relatively prime. It does not mean there won't exist a solution. It's just that Chinese remainder theorem can't guarantee. As you can see in this case, there's not going to be a solution. This thingy says x is odd. This says x is even. They completely contradict each other. It's still possible that there could be a solution. And if there is a solution, then you would likely have to break it up. Like, for example, if we had this. Then, in this case, there still is a solution. We could see, okay, x equals 4 mod 6. We already have 4 mod 8. So maybe you can split this up as x equals 1 mod 3 and 0 mod 2, right? Just like how we can combine them, often it's a good idea to break it apart and break it up into separate primes. So you don't have to deal with 5 and 8 as mod 40 combined. You can deal with mod 8 and mod 5 separately. So 1 mod 3, 0 mod 2, we broke it up. But 0 mod 2 is already given by this condition. So we're like, okay, this is redundant information. And now we can use CRT with this. CRT guarantees a solution. And oftentimes, it's a good idea to use CRT to break it apart, like I mentioned earlier. Let's go back here. Let's say we're trying to find the value of 2 to the power of 107 mod 72. Or let's take a slightly simpler example, maybe. Let's just say 15, right? So one way of doing this is with Euler's Cauchy theorem, right? You use general n. But another way that might give you a slightly stronger result is if you do CRT. So what I mean by that is you separately find 107 mod 3 and 2 to the 107 mod 5. And then using these two values, whatever you get, you know what, let's actually do it really quickly. So 2 to the 107 mod 3. We have 2 squared is 1 mod 3. This is just 2. 2 to the 107 mod 5. We have 2 to the 4 is 1 mod 5. So this is just 2 cubed mod 5 or 3 mod 5. Now, we can do a little bit of guess and check and combine these values of 3 mod 5 and 2 mod 3. And I believe you'll get an answer of 8. So 8 mod 15. And you see how, again, we could just use the Euler's Cauchy formula, but sometimes Euler's Cauchy formula might not be as good as just using CRT. So CRT might tell you it cycles every, let's say, in this case, CRT tells you that, notice here, it cycles every 2, and over here, it cycles every 4. So clearly, if it cycles every 2 in the prime for 3, and cycles every 4 for the prime 5, it's going to cycle every 4 for 15, the LCM. But Euler's-Totschen theorem gives you a slightly weaker result. It tells you that, let's do it. Totschen of 15 is what? Totschen of 15 is 15 times 2/3 times 4/5, 8. So Euler's-Totschen theorem only tells us 2 to the 8 is 1 mod 15. Versus CRT told us that 2 to the 4 is 1 mod 15. Euler's-Totschen theorem is not wrong here. It's completely correct. It's just that this is a much weaker condition than this is. And the reason is because Euler's-Totschen theorem is just like, okay, 2 times 4, now we multiply them, as in the Euler's-Totschen function. But when you do CRT separately for the primes, you can see like, okay, you don't need to cycle it every 8 in order to capture both primes. 4 is good enough. So oftentimes, a good strategy, when you're trying to find the value of something mod some giant power, break it up into the prime powers. So yeah, sometimes it could be a little bit more complicated, like 2 to the 107 mod 45. So in this case, we would break it up into 2 to the 107 mod 9 and 5. And then at the end, we can combine them again. So mod 5, you just use Fermat's little theorem. Here, you can't use Fermat's little theorem, but you have to use Euler's-Totschen theorem. So it's just like it's use Euler's-Totschen theorem, but instead of doing Euler's-Totschen theorem for like a combination of everything for a bunch of other random primes as well, we focus on Euler's-Totschen theorem when we just have prime powers. And this will give us this can sometimes give us a stronger result, like for example here. Okay, so this Chinese remainder theorem, it's useful and all. It tells us that there is a solution. Now, for small values like this, it's not hard to just guess and check, and eventually you'll get a solution. It's not that many values. But sometimes it's not that easy to guess and check, because of the fact that the numbers might be larger. So we have this strategy which is really only necessary. I mean, it's never needed, but it's really only beneficial when you have larger numbers. But just for the sake of demonstration, I'll show it for small numbers because it'll be easier to understand that way. Let's see, we have n is 5 mod 8, and we also have n is 3 mod 5. So I'll show you the general strategy of going about solving these. And the strategy is to use the algebraic form. So because a number can be represented as 5 mod 8, we can also say the number is a plus 5, where a is something. Similarly, we can say it's 5b plus 3, where b is something. Now take a look. 8a plus 5 is 5b plus 3. So now what we do to this equation is we take the value mod 5, because 5 is smaller. And what this gives us is now 3a, and then 5 goes away, is congruent to 3 mod 5. And now we can just divide by 3, you get a is 1 mod 5. So now what do we do? Now what we go and we see, okay, if a is 1 mod 5, it can be of the form 5c plus 1. So now we say 8 times 5c plus 1 plus 5 equals 40c plus 13. Aha! So this is just 13 mod 40. And this method works in general. And let's say we wanted to do 3 values. It's very simple. You just combine the first 2 and then combine these. Right? So this strategy is useful, but guess and check also works just fine in this small numbered case. So yeah, the idea is you convert it to algebraic form, and then we take mod of the smaller value. And there's another way which you just use general formula, which I have not memorized, and you do not need to, but if you want to, you can, right? This is a general formula using inverses and stuff. Feel free to look at this, memorize it if you'd like, but you really don't need to. Definitely not required. And yeah, if you're trying to solve a general with more than 2, just solve them 2 at a time. So yeah, just to summarize the strategies here, when you're trying to find mod of some large and random numbers, very good idea to split into the prime powers and then use Euler's Totient theorem or Fermat's little theorem if there's just a prime, and then you can find the values of mods separately and combine with CRT. Now sometimes you can just directly use Euler's Totient theorem. In fact, most of the time, and that will be fine as well for your purposes. So now we're going to move on to some algebraic number theory, which is, okay, this is really just Diophantine equations, so I think I'll just skip to this next section. It's really just this with a little bit of difference there. So, I mean, we already covered these factorizations in algebra, most of them, I think, besides Sophie Germain's. Okay, so let's just go over this one. X to the fourth plus 4y to the fourth is x squared minus 2xy plus 2y squared, and then x squared plus 2xy plus 2y squared. So the reason this works, difference of squares. X squared plus 2y squared minus 2xy, and then x squared plus 2y squared plus 2xy. But take a look, by difference of squares, this is just this squared minus 2xy squared. And this will just become, if you, I'm not going to do it, but if you expand out everything, it will just give you this. Because the xy terms, x squared, y squared terms over here will just cancel out. So that's why this is true. It's really important. And you especially want to be on the lookout when you see fourth powers or any multiple of fourth powers. So like 36th powers or 8th powers. In fact, there was this Amy problem that completely telescoped with this. Okay, so Diophantine equations are just integer equations. The key thing about Diophantine equations that make them different from regular equations is you know the solutions are integers. This, you cannot neglect this fact. You have to remember this. So how do you solve these Diophantine equations? They're often much harder to solve than normal equations because now you don't have as many equations because you're given the fact that they're integers. You have to use that condition somehow. So the first strategy is take mods of different numbers. For example, if you're trying to solve, okay, when is x squared equal to 2 mod 3? Or, you know, if you're trying to solve some random equation, like find how many solutions satisfy something like this, right? Or find what values. Oftentimes, when you take mod of something, it gives us some really nice properties about it. For example, in this is like a nice standard AMC question that could happen. I mean, it's not hard to solve it by just looking at some small values, but just to demonstrate technique. What must be true about y mod 3, let's say, in this question? So you just take mod 3 of this whole thing. Take a look, x squared, right? When x is 0 mod 3, x squared is 0 mod 3. When x is 1 mod 3, x squared is 1 mod 3. When x is 2 mod 3, x squared is 1 mod 3. So take a look. Squares are always 0 or 1 mod 3. That's a super useful fact. So the question might be like, okay, solve this equation in integers, where you only have one equation but two variables. And then sometimes you can be, okay, take mod 3, and that will give you a condition about what x squared must be mod 3. And using the fact with that, you can use this, you can be like, okay, what are the possible values for x squared plus x mod 3? And then you can use that to find the values that could work for y. So in this case, you can see x squared plus x can be 0 mod 3, it can be 2 mod 3, and it can be 0 mod 3. But it can't be 1 mod 3. So those are the possible values for y. And of course, this is often useful because sometimes you might have bigger equations, like n to the 15 or something like that, where taking mods might make them simpler and give you restrictions. That's the purpose of taking mods. To get restrictions on what might work. Because here you're like, okay, anything could work. But then you're like, okay, mod 3 or mod 5 or whatever mod. Okay, now I know that, okay, only x equals 1 mod 3 values can satisfy this equation. And now I've restricted my search down to only 1/3 of the values. And so here's some key properties you want to keep in mind. This is actually like a very universal technique. It's useful and even like up to Olympiad level, this kind of meta strategy. So when you have squares, you always want to consider mod 3 and mod 4. So what mods you want to take in order to make your Diophantine simpler. When you have cubes, it's often helpful to consider mod 7 and mod 9. And those are like the main ones here. Because these are useful, because when you take these mods, there's a lot of restrictions on what x cubed is. So x squared is always 0 or 1 mod 3 and always 0 or 1 mod 4. So you see how that gives us a lot of information? Because x squared cannot be 2 or 3 mod 4. X cubed mod 7, well, what can that be? I believe it can only be, x cubed can only be -1, 0, or 1 mod 3, mod 7. And for mod 9, it's something similar, I believe. -1, yeah, I think it's the exact same. -1, 0, or 1 mod 9. So this gives us a lot of restrictions on what the value of x could be in these mods if you have cubes. You want to consider these mods. And that will be like, okay, x has to be this mod 7 or mod 9 when you have cubes. And then you might be like, oh, when x is 0 mod 9, there's only one possible value before x gets too big. And that brings us to our second strategy where you bound the possible values of different terms. So this is kind of, you know, this is very like a computational style technique where you see that anything bigger than 10 might not give me a solution. And there was this one question, I believe, I don't remember exactly what it was, but it was like x to the 2012 equals 2y minus y squared over integers. Find all the solutions or something, how many solutions there are. And then you're like, okay, 2y minus y squared has a maximum value by difference of squares, or by completing the square. And x is 2012 is, if x is even more than like 1 or 2, it's going to be giant. So this gives us very few possibilities, because if x is even 2, now this side is already way too big, and way more than the maximum this side can possibly be. So bounding both sides of your Diophantine. Factoring, using factorizations, difference of squares, difference of cubes, sum of cubes, binomial expansions. Oftentimes we're going to have to use our previous techniques we covered. Like for example, we could have that like this, 2 to the n minus 1, 2 to the n minus 7. And we're trying to find, okay, when is this equal to 0? When is this a multiple of 3? That could be a nice Diophantine equation, or a similar style problem, where you might have to consider, you know, standard or Fermat's little theorem stuff. Okay, when is 2 to the n 1 mod 3? And when is 2 to the n 7, or 1 mod 3 for this as well, you know? And look for conditions on what must be multiples of divisors to rewrite it. So let's say we discover that, okay, A is 0 mod 3 from random problem. Now, it might be helpful to be, why don't we say A is 3A naught? So now we're kind of getting rid of this restriction and seeing what this might give us in our Diophantine. So a good strategy to keep in mind. Okay, now on to bases. So bases is just a different way of writing a number. You have, let's say, base 5, for example. If let's say we have 123 base 5. It's just a different way of regrouping. So this is 1 times 5 squared plus 2 times 5 to the 1 plus 3 times 5 to the 0. So you know, if this was in base 10, our normal number, it would be 1 times 10 squared plus 2 times 10 plus 3. Now base 5 is just, we regroup every 5 instead of every 10. And we can also have decimal bases, because now let's say we have 1.5, let's say base 3, or you cannot have a digit exceeding the base in base numbers. So let's say 1.2 base 4. What is this? Well, first of all, we just have 1 times 4 to the 0 plus 2 times 4 to the negative 1. This is 1.5 in base 10. So you see how it's the same thing, except now we go to negative exponents. Okay, so now here are some more miscellaneous concepts. Chicken McNugget theorem. So like, let's say you have some item. What's the maximum amount of money that cannot be created with 3 and 5 cent coins? So what this is saying is that after a certain point, every value you can make with 3 and 5 cent coins. In the beginning, there's going to be many holes. There's going to be many things you can't yet make. Because like, for example, 1, you can't make 1 cent. 4, you can't make 4 cents. 7, you cannot make 7 cents. Eventually, there's going to be a maximum amount of money you can't make. And the formula for that, it's pretty simple. It's just AB minus A plus B. Okay, now Legendre's theorem, the number of factors of P and N factorial. Well, this is like a standard math counts level technique, like 37 factorial. How many factors of 5 are in the prime factorization of this? Well, it's just a very simple technique. You just do 37 divided by 5 with 7, and we ignore the remainder. And then we go 7 divided by 5 is 1, and we ignore the remainder. 1 divided by 5 is 0. Again, we're always ignoring remainders here. And then we just add these all up. That's like the standard trick for Legenders. And the reason is because from 1, 2, 3, all the way till 37, the number of multiples of 5 in this factorial expansion is going to be 7. The number of multiples of 25 in this expansion is going to be 7, which is the number of multiples of 5, right? 5, 10, all the way till 35. But the multiples of 25 are going to be only 1/5 of these, or less than 1/5 of these in this case, because we have 7 multiples of 5, right? 5 times 1 all the way till 5 times 7. So, right, we're just looking for 7 divided by 5, and it's just going to be 1 in this case because we don't care about the extra 2 values, 6 and 7. That don't give us any multiples of 5. And finally, we do 1 divided by 5. I mean, we get 0, so there's no multiples of 125 or bigger. Now we just add everything up. Okay, and now we're finally on to geometry. Let's now talk about geometry, starting off with angle chasing. And the basic angle chasing formulas you probably know. Sum of angles in a triangle, line 180. Of course, isosceles triangles, 2 angles equal, sides are equal. And complementary angles, sum to 90. Supplementary, sum to 80. And, vertical angles, these are equal. And these are equal. And same thing, we have corresponding angles are equal. And from that, we derive a bunch of other relations like alternate interior angles, for example. And oftentimes, we have these kind of nice little tricks where, let's say we somehow prove with our angle chasing that these angles are equal. That also means these lines are parallel, right? Now, obviously, you'll never get a super simple angle chasing problem like this on the AMC 1012. So oftentimes, the strategy you might have some complex angle chasing problems where you have a lot going on. And a strategy that I like to use is just call one variable x. Label something x, and maybe you might also label y. And you can use as many variables as you need. And now what you do is you just go and find all the angles in terms of x. Ideally, you want to have just one variable. Sometimes that might not be possible. So you might be like y. So sometimes it's possible, let's say a problem asks you find the measure of this angle. You just go angle chasing. You write parallel lines, this angle, and you just get your answer. Sometimes, though, you might also have to use things about circles, so like cyclic quadrilaterals and inscribed angle theorem, but we'll cover that stuff later. And sometimes you may not just be able to use angles. You might have to do some similar triangles or extend some sides. And last year's AMC 10B, 2023 AMC 10B number 20, is a classic example of an extremely tricky angle chasing problem where there's many solutions, but the trick is you sometimes want to spot different things which are not just like, these basic identities. We'll talk about those things later, though. Okay, next, some basic polygon stuff. Sum of the angles in a polygon, n minus 2 times 180. In a regular polygon or equiangular one, this is going to be the interior angle. Exterior angle, 360 over n. And from that, it's actually easy to derive this. And some common values here. It's often very helpful to memorize these, but it's not necessary. It can just save you a little bit of time. Okay, so now inscribed angle theorem, right? We have this angle inscribed, half of this arc angle, or the central one. And yeah, when you have a right angle, it's going to form the diameter. So here's something very important to know about right triangles, which you probably know, but it's important to be aware to look out for this. Whenever you have a right triangle and you have the midpoints, you should immediately be reminded, midpoint of the hypotenuse in a right triangle, even if it's not given in the problem, this is equal to this is equal to this. And this is actually used on that problem I was talking about earlier. Okay, now chord. So yeah, it's just a line through a circle, really between 2 points. A cool thing about chords is that if you draw the perpendicular bisectors, we can draw the perpendicular bisectors of this. So that's often a really common strategy. So yeah, chord, this is also kind of going to lead into power of a point. But you draw this, we have this equals to this. Oftentimes when you have chords, dropping this perpendicular is a very good strategy. Why is it a good strategy? Because now take a look. Now, this chord, we can deal with it in terms of the radius, right? Otherwise, it's just this random line. But now once we drop this perpendicular, now we're relating it to the center of the circle and also draw these radii. Okay, so now here are some kind of other cool theorems which are really important to know. So yeah, congruent chords are equidistant from the center of the circle. So if two chords have the same length, they're going to be the same distance away. Why is this true? Well, let's say this is x. Now this distance is just square root of r squared minus x squared by Pythag. But then you also have to remember that the same thing is going to be true for any other chord in the same circle, because r is constant. And also, if they are congruent, they also intercept the same angle. Meaning, for example, this angle, if these two chords are the same length, this angle is equal to this angle. A very useful thing property. So I've seen several problems that use a technique before where they have a triangle, and here's a good cool example of it. Something like 5, 7, 7, 5, let's say, right? And let's say you have this, and you're like, okay, find the circumradius of this circle. So there's this really, really neat trick that we can use here, and it's something that I find really, really cool. So imagine you have all these pieces. We have this piece, this piece, this piece, and this piece. So what we can do is imagine we just take this piece and move it here. We rotate it here. And then we move the 5 piece over here. Well, what will we get? Let's see. So copy and move that aside. And then let's paste that over here and see what happens when we flip those two arcs. So we rearrange these kind of circular segments. So we were flipping this piece, we're moving it here. And we take this piece and we move it here. So then we get, let's see what we get. 7, 5, there, like that. What is this? It's a rectangle. So now all you have to do is find the radius of this, which is quite simple, right? Again, we use the same property. We draw this hypotenuse, we draw this radii, and take a look. Because of our property from earlier, this is just going to be half of the hypotenuse, which is this, right? So a really cool trick, right? We rearrange the circular pieces. So that's something you can keep in mind. Okay, now we have this over here. The angle marked here is going to be half of the difference of these two arcs. And the proof of this, well, I'm not going to go into it, but it always involves constructing the center and then doing some stuff with inscribed angle theorem. You can work it out on your own. It's a good angle chasing exercise. Next, we have this identity over here. All it says is that this angle over here in the center is just the average of these arcs. Another useful property. And then now over here. Now this is so useful and so important. So let's for a moment take a look at tangents. So imagine you have a circle. Whoopsies. A circle. And you have a tangent. So what's something you immediately know about this? Well, if you construct the center, they form a 90-degree angle. Right off the bat, something you have to know about tangents. 90-degree angle. So that's the first thing you know about tangents. The second thing you know about tangents is, let's say, I want to find this angle. A really cool property is that this green angle is just going to be half of this arc. When you're tangents, number one, immediately draw the radii and draw a 90-degree angle. That should be the first thing that comes to mind. But second, this property, which is a little bit more nuanced, is basically saying that this angle is half of this arc. But take a look. Now let's say we got something like this. Now oftentimes, and so, let's just say something like this. Now what do we know about this triangle and this triangle? They're similar. Why? Because this angle is half of this arc. This angle is also half of this arc by tangent property. And this angle is shared. So this is like a kind of a common configuration in these types of problems. So it's a really good thing to keep this in mind. Okay, now let's move on. Oh yeah, that's one more really cool trick let's go over. So let's say you have like a regular, I actually have a short of this on my channel if you're interested. I covered this example. Let's say you have this kind of octagon, and then you have and you're trying to find, let's say, this random angle. It could be whatever. Let's say, or maybe not that, that's too simple. Let's say you're trying to find this, right? This random angle, any polygon. So doing it just like this is actually not easy because you can find this angle, subtract. I mean, yeah, but now what happens when the polygon is 14-sided, and it's an even weirder angle. Now here's a cool trick you have to remember for these types of things, and that is draw a circle around the polygon. And I know that my drawing was not good here. Okay, let's try. But imagine you just have a circle that you circumscribe this polygon around. Now what's going to happen is that using the circle property, we know that because it's a regular polygon, we can have a circle around it. It's symmetric. So now take a look. This is just an inscribed angle in the circle. It's half of this arc. But now what is that? What is this arc? Well, to find that, there's 360 total degrees in the circle. There's 360 total degrees in the circle. And there's 3 parts of the 8 parts of an octagon here, right? Remember that thing we learned earlier? When there's equal chords, which is true because it's a regular octagon, these angles are all equal for all 8 sides. So this thingy is just going to be 3/8 of 360. So times 3/8, which is, well, we can cancel that out, 135. So this angle is 135, and this will just be half of that, 135 by 2. So whenever you have these kind of regular polygon angles, just draw a circle around it. And then you can use inscribed angle theorem pretty neatly. Okay, right angle tangency point. Yeah, this is something you have to do. Whenever you're given, oh, this line is tangent, well, there's kind of a few things I mentioned earlier, but you have to draw this. And another thing to keep in mind is power of a point, which we'll talk about later. Okay, now cyclic quadrilaterals. Now this is actually trivialized AMC problems in the past. And the property is if you've got 4 points and they're all lie on a circle, the sum of opposite angles is 180. So something that's really cool is, let's say you didn't even know that there's a circle here, but you somehow found out that these angles sum to 180, or these angles sum to 180, either one. Now what you can do is say, we can just draw a circle around this. These 4 points will lie on a circle. We don't know what the radius of that circle will be, but we know that the term we use here is concyclic. They all lie on a circle. But notice that that's not true for every quadrilateral. Like, for example, we might have something like this, but there's no circle that passes through all 4 of these points. So only quadrilaterals that have sum of opposite angles 180 are concyclic, or are cyclic. And we say 4 points are concyclic. So cyclic quadrilateral properties. So oftentimes, and now here's just some meta strategies, right, when you're approaching these types of problems. So whenever you have these circle problems in AMCs, you often have, you got a bunch of them. Like, I remember there's like something like this, or there's many different circle problems. The number one strategy is always draw all important radii. And by important radii, I mean draw the radii. So what is a circle really? This is a silly question. But a circle, if you have a circle in a center, is a set of all points that are equidistant from the center. So what does it mean when the problem says these points all lie in a circle? What new information does that give you? The only thing it's really telling you is that, okay, points B, H, F, G, these are all equidistant from center. So that's why I always like to say, use this information, right? Let's say in this problem here, we got a square inscribed here. This point, the circle is going to tell us that these 2 points are equidistant, and sometimes we might even be given the radius, but just for the sake of demonstration here, let's, this thingy, we're given that these 2 lengths are equal, and sometimes that might be given, sometimes not. So we draw those radii. And similarly over here, we draw the center. I know these are not exactly the greatest circles. We draw all important radii. So always, whenever you have a circle, connect the center to all defined points. So for example, drawing this radii, I mean, sure, it tells us that this length is also equal to this and this, but what is this point? This point is meaningless in our diagram. So draw all the radii that connect your center to well-defined points, like these 2, for example. That's a strategy you have to use whenever you do these circle problems. And sometimes you can kind of get past that. You may not always need to, but this cyclic quadrilateral thing is kind of the same thing, where sometimes, drawing the centers, the radii is really important, but sometimes there's like a shortcut to doing that, where you don't necessarily have to draw all the radii because you'll get a lot of information from this cyclic quadrilateral condition. And yeah, this will also help in angle chasing all of these circle theorems. Okay, area of a triangle, the most simple one, you guys know. Let's now discuss a really cool property of triangle area, which is immensely useful. So let's say we have a triangle like this, and let's say we have a line here. Let's say this thingy is 2, and this thingy is 3. So, without even knowing what the height is, we can immediately tell the ratio of this triangle's area to this triangle's area is 2 to 3. Why? Because they both share the same height. They both have the same height, so the ratio of the areas is just the ratio of the bases. Now, this might seem obvious, but its applications are super important. For example, one standard application of this is, let's say we have another triangle here. Now, the question is, what is the ratio of the areas of this triangle to the area of the ratio of this triangle, this purple one? Well, we can do something very similar. Notice how we earlier found the ratio of this triangle to this triangle was 2 to 3. And by similar logic, because these two triangles share the same altitude, the ratio of this triangle to this triangle is also 2 to 3. So that means the ratio of this triangle to this triangle must also be 2 to 3 because of the subtraction. So that's a very powerful thing to keep in mind. And oftentimes you can use area ratios to find side length ratios as well. So always remember that this implies area ratios. And another thing is that a very good strategy in problems is often to find the area in two different ways. So a pretty standard example of this is if you have a triangle, you're given the side lengths, you can find the area, and then you can be like, okay, area, which is given by Heron's formula, is also equal to half base times height. And base in this case is c. So we can solve for the height from here to there. And just considering the area in two different ways also allows us to find in radius. We'll talk about this later, about in radius and circumradius by considering the area in two different ways. Now, Heron's formula, this is also super useful if you have sides A, B, C, and semi-perimeter, which is just the perimeter divided by 2. The area is square root of s times s minus a times s minus b times s minus c. And in center of a triangle is the intersection of all the angle bisectors. So you draw all these angle bisectors. This is going to be these two are equal, these two are equal, these two are equal. You intersect them all at the in center, and it's the center of the inscribed circle. And yeah, something cool to note here is in center is just area over semi-perimeter, just by this. And a cool thing is in a right triangle, and you don't have to memorize this, but you should know how to derive it if needed. Let's say you have an incircle, right? Let's say this is R. Take a look. Because this is right, these angles are 90, and it's a right triangle, so that's 90. And therefore, this is 90. So this is R, this is R. So then, if you can find this length in terms of the sides, that would be really useful. So then what we can just say is, let's just call this side A, this side C, and this side B. Now we have that side length over there. Well, notice here, this thingy is equal to this thingy. This thingy is equal to this thingy. And what is that? Well, let's see. That's just A minus R. That's B minus R. So we have A plus B minus 2R is C. So from here we solve for R, we get this quantity. So a good thing to keep in mind for right triangles, you should know how to derive it if you don't memorize the formula, but you can find the in radius from the sides. Now using in radius, yeah, we discussed this already. And yeah, you can, if you know the area and semi-perimeter, you can find the in radius. Okay, now circumcenter. Now this is actually much less known. And that is the area of a triangle in terms of the circumradius is ABC over 4R. Now, something cool here is that we can also write the circumradius equals ABC over 4 times the area of the triangle. And you can oftentimes, so let's say you're given the sides, you can find the area of the triangle with herons, and then you can plug this in to find the circumradius. Yeah, similar to the inradius, where if you know all 3 sides, you can find the area using herons and divide by semi-perimeter. So what we've now discovered is with the 3 side lengths, we're unstoppable. We can find the inradius using RS. We can find the circumradius using this. Heron's formula along with these theorems are really powerful. And Shoelace will come back to this later, don't worry. We'll cover it in coordinate geometry. Okay, now we have this medial property, which we already went over. In a right triangle, you have to know this. And sometimes, in fact, if you, let's say you know that this length is equal to this length is equal to this length, you can do the opposite. You can now say, okay, this is right. And Stewart's theorem, or first centroid of a triangle, see how we intersect the medians. It's going to be 2/3 of the way up. So this to this is 2 to 1. This to this is 2 to 1. And this to this is also 2 to 1. And Stewart's theorem, now this is a very advanced theorem. It's likely going to be only useful for those last few problems. But for those of you who aren't on that level, you can learn this theorem. It can be useful. And for those wondering, you can just derive it with the law of cosines applied on this triangle and this triangle. That's like the proof. You can do the proof if you want. So the acronym here is a man and dad throw a bomb in the sink. That's like the acronym to remember this. And the reason is because it's like MAN plus DAD equals BMB plus CNC. So that's how you remember this. And the thing you say A, B, and C. And the way I remember it is N is on the same side as B, and M is on the same side as C. You're like, oh, MC, math counts. Maybe that's a way you can remember it. Whatever works for you. And yeah, this is just the D, the CV, and length. So let's say, for example, we're given that this length, this length, this length, and this length, and this length. And we're asked to find what is this CV and length. You can use Stewart's theorem. And here's a kind of a cool corollary for angled bisectors. So let's say now we have a new triangle. And now let's say we're given that these two angles are equal. So we have this cool thing. MN plus this thingy squared, D squared, equals B times C. And that has actually saved me some time on the AMCs in the past in these problems. So it's something, it's good to remember. But how is it derived? It's derived from this original Stewart's theorem and angle bisector theorem, which I believe we'll talk about in a minute. Now here's another thing. If AD is a median, then you have this formula here. I haven't memorized this, and you can if you want to. It could be useful, but you know, you can always just rederive it from the original Stewart's if you need to. So now equilateral triangle, pretty simple stuff. A. This length is A over 2. And then we get height is A root 3 over 2. Area formula, gotta know it. Root 3 over 4 times side length squared. Right triangles, of course, we got Pythagorean theorem. I'm sure you guys know this, but some other useful properties is Pythagorean triples. So oftentimes you can save the work of having to do Pythagorean theorem using these Pythagorean triples. So some common ones you should know. Basically, these 3 sides form a right triangle are these ones over here. These are like the most common ones. And a cool property is that lets you multiply all the sides by 2. It's still going to be a Pythagorean triple. Why? It's the same triangle scaled up. Similar triangles. And I've actually got a whole video on my channel covering Pythagorean triples along with a really neat trick. That's maybe a little bit beyond, but you can learn it. It's a really cool thing to know. It can be useful. But this is like the absolute basics. You have to know these Pythagorean triples. Yeah, 45, 45, 90, you know, A root 2, area is just half base height. 30, 60, 90, A root 3, 2A, and yeah, you can get the area pretty easily. And then 13, 14, 15, this is a little bit more unique. If you have 13, 14, and 15, what you can do is drop this altitude over here, and this altitude has length 12. And now take a look. Pythagorean will tell us this is 5, or Pythagorean triples. And then we get this is 9. And another thing is the area is 84. So neat thing is that we have this Pythagorean here and this Pythagorean here. Cool. Similar triangles, yeah. This is literally the most important geometry concept in the AMC 10 AMC 10 and 12 in my opinion. So yeah, of course, for similar triangles, you have the same angles, ratio of the sides is the same, and area is the side length squared ratio. And they're similar if the angles are the same. there's a bunch of similarity rules. You're probably familiar with this AA similarity, where the two angles are the same. SES, two sides are the same ratio, one angle is congruent. Three sides have the same ratio. HL, so the hypotenuse and leg have the same ratio. And LL, the two legs have the same ratio. And be careful about SSA. If you have like S and then S, for example, here's the reason why it doesn't work. Let me draw that better. So let's say we have this. Take a look at this. Take a look at the two triangles in the figure. This one and this one. Notice that they share an angle. They share this side. And they also share this side because they are both equal. But they're clearly not similar in this case. Or we're going about similarity here. But the same thing is true for congruence. SSA does not work. Yeah, some basic similarity stuff you're probably familiar with. But you know what's... This basic stuff is, just basic theory. That's not the hard part. The hard part is spotting these hidden similar triangles. And that's so common, where it's not like, oh yeah, if two lines are parallel, if this is 3 and this is 4 and this is 5 and this is 6, find this length. No, it's never going to be that easy on the AMCs. The similar triangles often require angle chasing in order to prove that triangles are similar. So how would you do that? Well, there's different angle chasing relations you can use. Like parallel lines is the simplest one. Oftentimes circles are often really useful. And sometimes you might not even be given directly the similar triangles. You might have to construct them yourself. So that's the hard part of similar triangles. Not like the basic theory, but the applications of them. And let me just show you one kind of cool example of similar triangles on a past AMC concept. I'm not going to go through the whole solution, but I've covered this on the channel before, by the way. So you can check the video out if you're interested. But yeah, so we got here. We have this. So in this problem over here, we were given that this thingy is 15, this length is 15, and this length is 30. And the idea here, which I'm not going to explain the full solution in detail, but the idea here was to construct this altitude. Why? Because now this triangle, and this triangle are similar. So what does this tell us? This tells us that this part is exactly half of this part. And that gives us so much information about this that we didn't already know. So oftentimes you draw a perpendicular line in order for similar triangles to work. Right? So you sometimes construct your own similar triangles by dropping perpendiculars. Let's take a look here. We got similar triangles. Now another strategy which is equally as difficult is drawing parallel lines. Now this is slightly rarer, but if you look at many contests, this is still very useful. So for example, let's say we've got over here something like this. I don't know. And let's say we have the midpoint over here. And we draw this line. So and let's say we're given this altitude or something like that. So I'm not doing any specific problem. I'm just trying to show general strategy. So let's say you're just trying to find this length or something, right? So a really good strategy is you can be like, this length, this is a midpoint. But what if I construct a parallel line like this? Take a look. That's the altitude of the triangle. So this thingy is just going to be double of this. So now instead of finding this weird length, we just have to find the altitude. So a pretty cool trick. When you see, sometimes you construct parallel lines in order to form similar triangles. So similar triangles are everywhere. There's, number one, it's obvious. Basic angle chasing gives you the solution. Number two, it requires some tricky angle chasing. You use cyclic quadrilaterals maybe. Maybe you do some stuff about inscribed angle theorem. It takes a while, but you realize eventually, oh, this is similar. And this is like, okay, this is easy. This one is medium. You can do it, but it requires a little bit of work. And now the hardest part, which many people struggle with, is when you have to make your own similar triangles. And that's what I just showed here. Constructing perpendiculars, constructing parallel lines, etc. And this is hard. And oftentimes, even like the hardest AMC problems use this. Constructing your own similar triangles by dropping perpendiculars, parallel lines. Okay, so now let's move on to some special properties. These ones are just derived from similar triangles. So what do we have here? Right, so we have some cool properties. This thingy times this thingy equals this squared. And that's useful often. And another thing is that this times this is going to be equal to this thing squared. And this times this is equal to this thingy squared. So you can remember it is everything starts at A. So we have AD, AC. AD times AC is AB squared. And same thing for C. And then D, everything starts at D. DC, DA is DB squared. That's how you remember it, right? Everything starts at A for this one. Everything starts at C for this one. And everything starts at D for this one. Okay, now moving on to angle bisector theorem, which is so useful. You have to know this. If you have this angles are equal, we have that this side length over this equals this over this. And the derivation is pretty neat. I'm not going to go through it, but it involves... Actually, you know what? Let's go through it. It's a really neat exercise in the art of constructing your own similar triangles. The idea here is we want to drop the altitude. Because, take a look. That's another sign to use similar triangles. We have this common angle. So what if we drop altitudes over here? And take a look. Now we have similar triangles here. We drop the altitude to 80. You know, it's not necessarily on the line segment, but it's still perpendicular. These triangles are similar. So now here we got a root. But take a look. We also have these triangles are similar. So let's just go through the proof quickly. We have, let's call this length, we have BD over, let's call this X, over X equals CD over, let's call that Y. And now, from this pair of similar triangles, we also have X over AB is Y over AC. So now, from this equation, we get BD over CD is X over Y. And from this equation, we get X over Y is AB over AC. Aha! And that gives us angle bisector theorem because we set these equal. So the idea here, we have this common angle, and that's, we should be like, I have one common angle. If I can just get one more, I have similar triangles. So then we're like, why don't we drop this altitude to get this right angle that's common? But then, cool, we get another pair of similar triangles from here. These two. And that ends up proving the angle bisector theorem. A super neat proof. Okay, so something else. Oh, this is some really basic stuff. Area of a square, rectangle. And the rhombus areas, half times product of diagonals. Perimeters, just 2 times d1 squared plus d2 squared, right? You just do Pythag on this triangle, and then you multiply by 4 to the hypotenuse there. And rhombus, we have these basic properties you probably know. Area of a parallelogram, just base height. Remember, the height is not this side. If you have diagonals d1 and d2, and now this is something a little cooler. We'll go over trig a little bit later, but this is d1, this is d2, this is theta. The area of this parallelogram, well, notice that these things bisect each other. So this becomes d1 over 2 and d1 over 2. And this becomes d2 over 2. You know what? We'll cover this in the AMC 12 video only. So let's move on now. Okay, area of a trapezoid, average of bases times height, circle, and the super basic stuff. And when you have a sector of 8 degrees, you multiply by a over 360 to the area and the length of the arc. Circle length problems, so draw all important radii. Remember this trick? You might have like a bunch of scenarios. Maybe you have something like a triangle inscribed in a right triangle. Whenever you have a circle, the first thing you should do, like before you even start thinking, okay, where's my center? Here. What are all the defined points? This, this, and this. And mark them R. That should be like the first thing you just do. You don't even think about it. It just becomes subconscious, natural habit. Because you'll see so many times in problems where you're just like, I have a circle here. And I've done this myself in the past, which is why I'm emphasizing this so much. Once I learned this trick of drawing all important radii, I was like, this feels so much more natural. So in the past, when you have a circle, you have this random chord here. And then you're just, you're dealing with the fact that you have a circle and you're confused. What do I do? When the trick was, you have to use the circle property. right? So draw them or important radii and you won't miss out on key information from the circle. Now, power of a point, again, something you have to know. So tangents are equal. That's pretty simple, right? You can prove that by congruent triangles. Power of a point inside the circle, we have this times this equals this times this. And something a little less well known is this fact over here. So let's call this center O. So it's this power, we can actually call this the power of P. And we say it's equal to this. Now something we also know is this power of P is also equal to R squared minus OP squared. So let's say you're trying to find this distance OP. Let's say you know the radius. Let's say the radius is 6. And let's say you're given that, okay, this is 3, this is 4. Or let's say you're given, let's say this is 3, and then this is 4. And you're like, okay, find OP. How can you do that? Well, take a look. The power of P is 3 times 4 equals 12. But it's also equal to R squared, 6 squared minus OP squared. So from here we get OP is equal to square root of 24, or 2 root 6. So that's the idea. If you want to find distance between this intersection of two chords and the center, power of a point and using this property might help. And we've got something similar for outside a circle. PA times PB is PC times PD. And make sure you don't write PA times AB. It's a silly mistake many people make. Everything starts at P. Always, always, always. PC times PD, not PC times CD. Never dealing with CD here. And for here, you see how it's kind of flipped. Over here, we had R squared minus OP squared, because you could be like, oh yeah, of course, OP is tiny, R is big. Over here, OP is big, R is small. So we do OP squared minus R squared. And in general, you could generalize this by just saying absolute value. That works completely fine. But here are just two separate cases for simplicity. And yeah, we can do the same strategy if we're trying to find OP, and we know the radius is 5, and we know this is 3 and this is 5. Well, what would we do? We could just use power of a point. And again, make sure if they give you this distance, you add the total distances to get PB. You don't just use AB distance. So especially when you're dealing with chords, power of a point is so useful. And of course, the theorem itself is not very hard. The application is the hard part. And oftentimes oftentimes it just helps to consider power of a point when you have a bunch of intersections in a circle. It gives you distances. Another example might be if you have like a circle, and then you have a square, and you've got a line going through the square. Well, take a look. Intersections of chords in the circle are your sign to use power of a point. You have this times this equals this times this. Or this times all the way here by power of a point. So whenever you got a bunch of lines in the circle that intersect, that's when you want to be like, okay, power of a point I should use. Moving on to cyclic quadrilaterals. Did we already cover this? I think we did. Well, yeah, we covered the basics about angle chasing. And another thing that's good to know is, let's say you have 4 points, and you don't know it's on a circle, like I mentioned earlier. If you prove that opposite angles come to 180, you prove it's cyclic, but something else also exists, and that is, let's say you prove that this angle equals to this angle. Take a look. This is just inscribed angle theorem. So this will actually tell us the opposite as well. It tells us that these 4 points lie on a circle. So if these two angles are equal, just like how if they were in a circle, they would tell you these are equal. These being equal tell you they're on a circle. So it kind of works both ways. In fact, I think most theorems in geometry, at least for our purposes, they're mutual. Like if they happen in one direction, they generally happen in the other direction. So that's something to keep in mind. And Ptolemy's theorem. Yeah, I know it's a little funny pronunciation. I used to keep saying Ptolemy's in my other videos. So yeah, there's a cool thing here. If a quadrilateral is cyclic, the product of these diagonals is just equal to the sum of the products of the opposite sides. So if like you do AB times CD, and then you add AD times BC, and then it's equal to BD times AC. Now there's an extension of Ptolemy's, or I said it again, extension of Ptolemy's called Cauchy's theorem, but that's beyond the scope of this. You can check it out, search it up online if you're interested though. Now, Brahma-Gupta's formula tells us the area of a cyclic quadrilateral. And it seems oddly similar to Heron's formula, you might wonder. So the area is just, you find the semi-perimeter, just the average half of the perimeter, and then you just plug it into this formula, right? S square root of S minus A, S minus B, S minus C, S minus D. And you take the square root. But be careful, this only works for cyclic quadrilaterals. When the quadrilateral is generalized, there's some extension of this, but quite frankly, it's super complicated and it's just really not easy to work with. So this is good enough. If you have the cyclic quadrilateral, sometimes they might combine Ptolemy's, Brahma-Gupta's, and angle chasing. So you might be like, okay, angle chase to be like, oh wow, this quadrilateral is cyclic. Oh, but then using the cyclic quadrilateral, I can now find the side lengths of this quadrilateral. And finally, using the side lengths, I can find the area. So oftentimes you'll get these multi-step problems on the AMCs, which have many steps combined. And polygons, I'm not sure why there's duplicates here. Oh yeah, maybe because now we're talking about hexagons and stuff. So yeah, this stuff is pretty simple. It's just derived from our previous formulas. The area of a hexagon, it's a neat little thing. You divide into 6 equilateral triangles. Each has side length that is the same as the side length of the hexagon. Okay, octagon, again, these are just derived from our angle chasing formulas. To get this, it's a pretty neat proof, which I talked about in the polygons video in more detail. But if you just reviewing it, here is what it was. Basically, you're like, okay, this is x, then this is x over root 2, x over root 2, and similarly here. So now we just find the area of the square and subtract the area of these triangles. Yeah, so you can memorize this if you want, but it's not hard to rederive. So cube, basic stuff, and space diagonal, root 3 times the side length, and you can derive this from Pythagorean theorem twice. So you can get a root 2 over here, and then using a, you get a root 3. Pretty simple. And rectangular prism, just use Pythagorean theorem to get the space diagonal and some basic formulas. This one is just from the fact of area of a formula for all 6 faces. Cylinder, volume pi r squared, surface area is just 2 pi r times r plus h, right? You find this thingy plus this thingy, unfold into a rectangle, 2 pi r and h, if you ever forget that. Okay, now cone. Now this is where it starts to get interesting. The volume, just 1/3 pi r squared h. The surface area is pi r squared plus pi r s, where s is the slant height. Not the height, but the slant height, which is nothing but the square root of h squared plus r squared by the Pythagorean theorem. Now there's a super neat trick with cones, and that is you can unfold them into a circular arc. So the idea here is we can unfold this cone into a circular arc. So there's sometimes a problem. An ant is all walking on a cone. It's trying to get from here. Let's say we have a simple example. An ant is walking on the cone. It's trying to get from the top point to somewhere that's here in this circle plane here. How do we do it? Well, a really good strategy is to unfold it into a sector, unfold the base. And the thing about this is that we have this angle r. So let's just say the radius of this cone is r, and let's say the height is h. So we have something cool. We have that this over here is the circumference of the cone, of the base of the cone. It's going to be equal to this. So this is going to be 2 pi r. Now what is this radius going to be? That's going to be equal to the slant height. So using these properties, you can derive some relationships, which I went over in more detail in the 3D Geo video, but I don't have time to cover all of that here. But using that, you derive some relationships. You can find this radius and this radius and this from those properties. And you can also find the angle. How? Well, you find this radius and you find this length, and you just backtrack using our arc formula. Yeah, so then you can just be like, okay, the ant goes from here to somewhere along here. Because if you unfold the circle, that goes here. So it's just going to be this radius. Pretty cool. So yeah, unfolding cone, often a strategy. Now moving on to sphere. Sphere, volume is just 4/3 pi r cubed, surface area 4 pi r squared. Tetrahedron, volume 1/3 base times height. And for a regular tetrahedron, there's something interesting here. We can derive this pretty neatly using some Pythagorean theorem stuff, where you draw the center and you drop the altitude, and you do some neat stuff with Pythagorean theorem, which I cover more detail in the 3D Geo video. You can derive this root 2/12 s cubed formula for a regular tetrahedron, And for a regular pyramid, it's something similar, except 6. Okay, yeah, so oftentimes it's not just going to be find the volume of a pyramid. Never. It's going to be like, okay, you have this complex polyhedron, you might have to break it up into pieces. Or, for example, you might have to, it happened last year on the AMC 10A, where they had this problem where they kind of cut off some corners a little bit from, and they had like this 3D octagonal cone or something like this. I don't remember exactly what it was. But the strategy I remember being, maybe it was a hexagon. But the strategy I remember was to extend this and form some extra triangular pyramids that we subtracted off from our volume. So we find the volume of something more and subtract off pieces. Okay, so that's about it for this stuff. Now cross sections. This is really the heart and soul of all 3D geo problems. So, let's just go here and discuss cross sections. So let's see, we have, I covered this so much more detail with many examples in the 3D geo video. So if 3D geo is something you struggle at or you just want to get better at, you definitely want to check out that cross section video where I covered this super powerful cross section technique in more detail. So these types of problems where they're like, okay, we got, for really any 3D geo length problem, we have 3 spheres and we've got another sphere sitting on top of it. Find the radius of this sphere or something like that. Where the strategy is you want to find a plane, so you just cut it through that plane. So, for example, in this case, you might consider the plane where you might consider the plane of where the spheres are, let's say, the centers of all the 3 bottom spheres. So that will give you this 2D version with a bunch of circles that are tangent. So the idea is we always want to make a 3D problem into a 2D geo problem. And you know what? Let me just go back to a simple example that I went over in the 3D geo video. I'm not going to cover it, but just for the purposes of reviewing this technique. The problem was you have this triangle that's inscribed in the circle over here. Triangle that's inscribed here. And we're trying to find, we were given the radius of this sphere. We're given this triangle has sides 15. We're given this triangle has sides 15. Oops, way too thick. This triangle has sides 15, 15, and 24. So, and we're saying the radius of the sphere is like something, I don't know, 30. I just made that up. I don't know if that's exactly what it was. So the idea is, what is the radius of the radius of the circle that's, what is the circumradius of that circle? Something like that, or I think. Or it was asking, what is the distance between the plane, this plane of this triangle and the center? So the idea here was you consider a cross section that cuts through this triangle. We have this 3D model, it's complicated and all. So what we do is we say, okay, I'm going to just slice all around like here. I'm going to take this up and open it up and see a circle. Now this has 15, 15, and 24. So what I can do is now find the radius of this circle. And then now, once I have the radius of this circle, whatever it is, I can use Pythagorean theorem along with this 30 and find the height, because this is 90 degrees. And this is true for many other problems as well, where we got a complex 3D situation going on, and oftentimes we take cross sections. Sometimes we got like a bunch of tangent spheres together. I remember we did some problem like this, where the idea is take a cross section that passes through the centers of these spheres, because that will say, if we take a cross section that goes through the center of a sphere, now it just becomes a circle. And another common thing to mention is that, there's another example we did earlier in the video, in the mastering videos. Cover these way more in detail and with examples and everything. The tangency point is always going to be slightly above. It's always going to be perpendicular to the surface, even then, in 3D. But sometimes people might get confused and be like, oh, it's going to be tangent in the same plane. So don't make that mistake. So, for example, in this problem here, there was this problem where we did use cross sections. It was really powerful and useful. We have like 3 spheres inscribed in a cone. They all touch the base and sides of the cone. Find the radius. So the idea here was you look at the centers of these 3 spheres and you take the cross section through them. And that will give us this diagram. And the cross section we're taking is through this. You can imagine we take this black region and we just cut it open and see what it gives us in 2D. And this is what it gives us. Each of these have the same radius. But then actually we realized in this problem that, oh, wait, they're not actually touching because the tangency point is not in the plane. You see how the tangency point is slightly above? It's over here. So there's actually going to be some gap over here. And this distance, which is going to correspond to this distance, is not going to just be the radius. So actually our circle, our cross-sectional circle is a little bit larger, where this distance corresponds to this distance. So yeah, some generals just take cross-sections, and oftentimes cross-sections through centers of spheres, a good technique. And if you're confused what I'm talking about, that's probably because you haven't watched the Mastering AMC 1012 video on 3D Geo. You're going to want to do that for sure. So, okay, area of complex shapes, this is similar. There's kind of two ways to go about it. You either break it up into smaller pieces or find something bigger and take off pieces. So like, for example, you could have, this is like a standard problem. Find the area of this region if this is a circular arc. You know, you just find the area of the triangle and subtract off this region. Sometimes you might be like, oh, we have a circular arc attached, and we have another circle on top, in which case you just add it up. You add or subtract depending on the situation. Sometimes you have to decide which one to do. Sometimes you might have to combine this with like Pythagorean theorem, power of a point, many of the other geometry techniques we've already learned. Yeah, this is kind of like, there's not much theory and stuff to cover here. Okay, now length of complex shapes. Yeah, drawing extra lines. Remember, like I mentioned earlier, parallel perpendicular lines to form similar triangles. Extending, oh yeah, I forgot to mention that earlier. Extending lines as well can also be useful. I don't know how I forgot that. Because let's say, for example, we got the square, and then we have this, and then let's say this. So, or let's say we're just given this. So a good strategy is we extend this line, and take a look. Now we've got similar triangles. This is similar to this. So don't be afraid to add new things to the diagram. Here we got similar triangles because of that thing. And dropping altitudes, so important. Let's say you want to find the area of a triangle. Oftentimes you just find the altitude. You're not going to be given it 90% of the time. You find the altitude using Pythag or other stuff. Dropping altitudes, super important technique there. Okay, line in a coordinate plane. Yeah, just simple equation of a line stuff in slope-intercept form. Slope, pretty simple. And yeah, this is something cool. If you have an angle here of theta, the slope of this line is just tangent of theta. The distance formula, you know, just Pythagorean theorem applied. You get this thingy. And then this is the most unique one we're going to do here. And let's just take a quick example. Let's say you have a point, let's say 3, 5. And let's say you have a line. Let's just say 2x plus 3y plus 5 equals 0. Now, very careful here, you write it in this form. ax plus by plus c. Never it should be equal to 5. No, you're going to make a mistake. Always, if you're given any other form, make it that form. ax plus by plus c. So now it's actually very simple, despite what the formula might suggest. You just write 2x plus 3y plus 5, but instead of x and y, you plug in the values of the point. So you put 3 here for x, and 5 here for y. And in the denominator, be very careful here. We take the square root of not 3 squared plus 5 squared, but 2 squared plus 3 squared. You look at the coefficients of the x and the y values, and that's going to be our denominator term. Be very careful, again, not the point in the line, the coefficient of x and y, the square root of that squared of a squared plus b squared here, right? A here, b here. Not x0, y0 in this formula. So yeah, don't get confused with this form, and this is the shortest possible distance. So, and you can actually derive this using some stuff. I'm not going to go into this here, but yeah. So, equation of a circle, pretty simple. You just try the circle and you get this. Shoelace theorem. Oh yeah, now we're on Shoelace theorem, and this is useful when you're trying to do coordinates. So let's just take a step back. Why are we using coordinates in geometry? So oftentimes, especially when you have a lot of right angles, let's say you've got like a triangle and you have like an altitude. So oftentimes, when you have a lot of right stuff, when you have, maybe you got a square, I don't know, maybe you have a square and you're dealing with something like this line, which is, maybe this is 2/3 of the way up or something. This is 6, this is 3. And you have another line and you're like, oh, how high is this or something. Oftentimes you can just assign coordinates. And the way you want to assign coordinates is make things simple. So for example, we can say this is 0, 0. Maybe we're given the side length of the square is 9. So 9, 0, and then 9, 9, and then 0, 9. So you want to assign coordinates, and then you want to be like, okay, what is the equation of this line? What's the equation of this line? Okay, I solve them, I get this point. And then now I can just be like, this distance, I can just look at the y value. See, when do we want to use coordinates? When we have right angles, so like squares, or you drop altitudes and we're looking for stuff dealing with this altitude. Maybe we have this altitude drawn, we're like, oh, what is the midpoint of this altitude? And then we're like, okay, what is this distance over here? So you could, of course, I'm sure there's a way with similar triangles, right? But another thing you could do is find the equation of the line that passes through this point and this point, right? And then we can find this point here by solving systems of equations. So sometimes you might often want to deal with this 0, 0, because that will lead to simple calculations. So a bit of a warning with coordinates: if you don't have right angles, it's not a good idea. If you got a bunch of random lines, don't overuse coordinates here. It's not going to help much. Okay, now we're going to move on to Shoelace Theorem. And basically this, what it does is it allows us to find the area of a polygon given its coordinates. So let's just take an example. We have 3, 4, let's say 0, 5, 2, 6, and then 1, 4. Just a random example. So the key thing about Shoelace Theorem is your points always have to be in order before you start. So the easiest way to do this is just quickly, roughly plot them. You don't have to be perfect. So like 3, 4, 0, 0, 5, and 2, 6. 1, 4. So now what we have to do is we have to go in an order of these points. So this is 0, 5. Okay, let's start with 3, 4. So 3, 4, then our order is 0, 5, and then 2, 6, and then 1, 4. You see how we're just kind of going all over the place? This will give us the area of this region, which is not what we want. We want the area of this region. So we have to go in order. We have to go in order of our quadrilaterals defined. And there's many possible orders here. One of them could be 3, 4, right? This is 3, 4. Then we have 1, 4. 1, 4, yeah, okay, roughly. Then we have 0, 5. And then over here we have 2, 6. So be very, very careful. If you're going to use Shoelace, put your coordinates in order. It could be, you could start at this point and go this way. It doesn't matter. It's just that you have to start at some point and go along the sides of the quadrilateral. Okay, so now you've written the points in order. And notice that when you have 3 points, it doesn't matter, right? Any order is fine. They all go along the sides of the triangle. And something cool is, let's say you have a quadrilateral like this. You're trying to find this area. So then you can actually do something cool. You can go in this order of this quadrilateral, and you'll actually find the area of this entire region. So a pretty cool thing with Shoelace there. Sometimes if you're given this kind of sum of two triangles, you can be like, huh, this is just like a kind of a silly quadrilateral. So I can just go in this order to get the area of this region. So now once you have this, there's a standard procedure in Shoelace, and that is you find the sums of all of these terms. You see how I start here, I go diagonally down, then here, and then here I go diagonally down, but there's nothing there, so I go up. And what I do is I find all of these products. So 12 plus 5 plus 0 plus 8. That's 25. Now, you know what? Let's just erase all of that. I'll rewrite that. So yeah, 12 plus 5 plus 0 plus 8. What we do is we now go the other way. So now we go this way and we find all these products. It's the same thing, just the other way, right? So let's see, we got 4 plus 0 plus 10 plus 18. That's 32. So now to find the area, what we do is we do half times 32 minus 25, which is 7/2. We do half of the difference between these two values. And it doesn't matter which order, right? We just take the absolute value of their difference and then divide by 2. This is our area. Pretty neat trick. Shoelace Theorem. And that's what this super complicated thing looks like, right? I explained it here. You multiply it like this and then like this. And you have this complicated way of writing it you don't need to worry about. Now, Picks Theorem, which is optional, but we'll still go over it. It's not that common, but it has come on some number 25s or some other problems before. And basically, you can find the area of any polygon by looking at the number of lattice points. So the thing here is, to find the area, you look at the number of lattice points that lie inside the polygon. Then you look at the lattice points that lie on the boundary. And then finally, you plug it in here. You do interior plus b by 2 minus 1. Intuitively, you're trying to find all the lattice points inside. But if a point's on the border, it's kind of like halfway inside, but halfway not inside. So you just do b divided by 2 plus I minus 1. And that gives you the area. It's not that useful, but it's good to know. Now, let's talk about floor and ceiling. So there's generally 3 kinds of techniques you can use for floor and ceiling problems. The first technique is you say x equals x plus the fractional part of x. Oh, before that, the floor of a number is just the greatest integer less than or equal to x. The ceiling is smallest integer greater than or equal to, and the fractional part is just a fraction. So like 1.67, fractional part is just 0.67. An important thing to keep in mind, for example, 1.67 has a floor of -2. You go down, it's not -1. And similarly, the fractional part is going to be 0.33. Because you can think about it like -2 plus 0.33. In general, the formula for fractional part is just x minus the floor of x. And oftentimes we can make this substitution in our problems. So if we have some floors and etc., especially if we're dealing with x minus floor, it's often helpful to consider this substitution for floor of x plus the fractional part of x. Now, when we expand stuff, that will give us some nice relationships because this has to be an integer and this has to be between 0 and 1. Okay, so then the next thing is use it to find an inequality. So the key thing is, let's say y is the floor of x. Then we can now say that x lies between y and y plus 1. Or in other words, x is going to be at least as big as its floor, and it's going to be less big than its floor plus 1. For example, 3.6 is greater than or equal to its floor, 3, and less than the floor plus 1, 4. Or another, and oftentimes ceiling is very rare in these types of problems. I don't know, it's called floor and ceiling, but really, we could just say floor, and that would be half of it. But ceiling is still good to know. There's oftentimes these kind of graphical problems on AMC 10 where you just have to be careful and plot stuff. And that brings us to our third point of graphing. And this is kind of the most intuitive and probably the most common things. These are more for like these later style problems which are useful. This is something that could come like even on some of the earlier problems where you just graph. And the floor graph, it looks like this, right? We have here and then a hole here. Here and then a hole here. So on, right? So oftentimes it can be helpful to consider the graph of things, and maybe you have an equation you're trying to do. You graph the two different things, and you graph the floor. It's easy to see it visually rather than trying to do everything algebraically. So this is like the most common technique, and it's often good for getting a hang of things. Okay, Okay, now we're gonna move on to inequalities. So starting off with the very basics, trivial inequality, x squared greater than or equal to 0. It's simple yet powerful. It's super simple, but it's so useful. And one example of it is when completing the square, right? If you complete the square like a times x plus b over 2a plus c minus c minus b squared over 4a, we see that if a is positive, then this has a maximum value when x is equal to negative b over 2a, and that maximum is this. Why? Because this thingy is always going to be at least 0. Now we have the opposite is true if a is negative because, right, we have when a is negative, this thingy is always going to be negative. So its maximum occurs when that term is 0 and its maximum is this. So these ones are a little bit more optional for the AMC 10, but you know, it still could be useful at times, so I still recommend you learn them. For AMGM, it just says the arithmetic mean is greater than or equal to the geometric mean. And we prove this, we can just square both sides, and we can actually factor it, we'll eventually get this thingy. So you see how the trivial inequality is being used to prove harder inequalities. Equality in this occurs when A is B. Okay, so now another corollary is the minimum of x plus 1 over x is 2, and that occurs when x is 1. So some kind of general remarks about it. The minimum value of a plus b occurs when a equals b, and the maximum value of a, if a plus b is constant, occurs when a equals b. So this is why AMGM is often very useful for minimizing sums and maximizing products. Because as you can see, we got products and sums. So that's kind of the general strategy. Just a quick example. Let's say we have x plus y is 10. What is the, let's say, minimum value or maximum value of xy? To do this, we just use AMGM. X plus y by 2 greater than or equal to root xy. And this is 5, so xy is 25, the maximum. And similarly, if you were given y equals 25 and asked to find the minimum value of x plus y, we could do the same thing. You could be like, okay, this is 5, so this is a minimum value of 5, or of 10, I guess. So that's a simple application of AMGM, and this can be generalized to n variables. So for example, we have like x plus y plus z all over 3 is greater than or equal to the cube root of x, y, z. And again, like you can use this to maximize sums and minimize products, this one as well. Okay, now weighted AMGM, which let's just take a really simple example of. Let's say we have x plus y plus z is 6. We're trying to find the minimum of x squared y, z. Or maximum of, remember, maximizing products. X squared y, z. So you could try using regular AMGM. You could be like, okay, product, the fourth root of this product is less than or equal to 2x plus y plus z all over 4. But this is not really a maximum. We know the value of x plus y plus z. We don't know this value. Because what are we going to do with 2x, right? We can rewrite this as 6 plus x by 4. But we don't want a maximum in terms of variables. That's no maximum. So there's a cool little trick we can do to get around this. And that is, let's just put x over 2 here. And then to compensate for this, we'll multiply by the fourth root of 2 squared. But take a look at this. Now it's just x over 2 plus x over 2 plus y plus z, which is x plus y plus z, or 6 over 4, 3/2. So from here, we can easily solve by just dividing by this thingy, which is root 2, and then taking the fourth power of both sides. Or yeah, this is now just, we can easily solve, or let's ignore this because this is not relevant. But from here, what you can do is take the fourth power of both sides and then multiply by 4 to get rid of this. And we would get our minimum or maximum of x squared y, z. That's weighted AMGM. Now on to Cauchy Schwarz. And the Cauchy Schwarz inequality states that we have x plus y plus z times x cubed plus y cubed plus z cubed. This is just an example. This is not general. And what it's saying is now take this term and this term. Well, you know what? Let's take a slightly more interesting example. Let's say you have this, and then now we have z to the 7 here, right? So what Cauchy Schwarz is saying is we can take this term and this term, take their geometric mean, or take their square root of their, just their geometric mean. This is going to be greater than or equal to, what is the geometric mean of x and x cubed? X squared. What about the geometric mean of y to the 5, y cubed? Y to the 4th. What about z and z to the 7th? Z to the 4th. And we take all of this squared. You see how we're like, okay, each term, now average them. These two terms, now average them, or geometrically average them, or average their exponents, basically. And then these two terms, average them. And then we get this quantity here. And of course, this is true in general. And it's written in this way, but a more natural way of writing it, in my opinion, is we have a1 plus b1 plus ... an, or whoops, that is not what I meant to write. a1 plus a2 plus all the way till an times b1 plus b2 plus all the way till a of n. It's going to be greater than, and now we just take the a1 b1 plus square root of a2 b2, so on, and now we just take all of this squared because we took the square roots earlier. And now we have two terms. We want to have two of these things on both sides. Okay, so when does equality occur? When is this an equal to sign instead of greater than or equal to? That happens when the ratio of this to this, or in our case over here, the way we've written it, a1 over b1, a2 over b2, all the way till an over bn, when those are all equal. Then this is an equal to sign. So sometimes, often in AMC problems, you might use this, be like, this is true. It's the same ratio. So we can use this equal to sign instead of the greater than or equal to one. And teaches how much is the corollary of this. It's not as complicated as it seems. Basically, it's just saying that now let's say we have a1 plus all the way till an. What we're going to do is multiply this by 1 plus 1 plus all the way to n times. By Cauchy, we get that this is going to be greater than or equal to a1 squared a1 plus root a2 plus dot dot dot, all of this squared. Do you see how it's just Cauchy, except now we have 1 plus 1 as each of our terms? Okay, now moving on to optimization problem techniques. This is just a review. We have trivial, AMGM, weighted, and Cauchy. Those are the main ones you need to know. And yeah, so some things are, it might be true, for example, let's say you're like, okay, x is greater than or equal to 5. But it may not actually be possible that x can be greater equal to 5. So you need to make sure that if you're trying to be like, okay, the minimum of x plus y is going to be 2 root xy by AMGM. You need to make sure that the equality case is always possible. It may not always be possible. So verify that the equality case of your inequality holds true if you're trying to maximize some quantity or minimize some quantity using our inequalities. And yeah, you can do that using the equality cases we mentioned before. So yeah, so let's say we're given something like that. Let's say you'll be like, okay, a1 plus all the way till a1 squared till b an squared. We're given that this times b1 squared all the way till bn squared is equal to a1 b1, so on. Take a look. This is the equality case of Cauchy. So what we can do is we can say that, okay, a1 plus b1 is equal to a2 plus b2, etc. So that's what this tells us. We can also sometimes use our equality case to see like, okay, this is just Cauchy in its equality form. So that tells us this cool thing. And also, for example, if x plus y is equal to 2 root xy, x and y have to be equal. And that is it for this video. If you enjoyed this video, be sure to subscribe and check out the Mastering AMC 1012 series. We cover all these concepts in much more detail and with many examples. Thanks for watching.